Okay, great. I think we're on. So good afternoon, everyone, and welcome to the third Monocular Depth Estimation workshop. So this is the workshop which is following the past two versions, one at the winter computer vision workshop and then at CVPR last year. Through this workshop, we'll have a group of invited speakers who will be talking about their work in monocular depth estimation. And we'll also be discussing challenge winners for monocular depth. The depth estimation has become a pretty crucial problem for the robotics community to solve, and it's been one of the primary problems that a lot of us have been focusing on. Over the last couple of years, monocular depth estimation has advanced substantially due to the availability of compute, as well as a lot of data, both labeled and unlabeled, as well as new technologies and new algorithms and models coming into picture that are making this even more exciting to work in this field at this moment. This workshop is basically going to be that platform which we thought would be interesting to get like-minded people together and discuss the monocular depth estimation overall. We've been fortunate to be interacting with a lot of experts in the field, and a few of them will be presenting their research here today. We also have a challenge, just to give everyone a brief on the challenge. The challenge is basically a benchmarking problem which was carefully curated for natural scenes. What we observed is a lot of the current monocular depth estimation challenges are focused on autonomy. So we wanted to give another perspective using natural images, which would have indoor and outdoor scenes. So with that, let me introduce the organizing team. So I'm Ripudaman Arora. I am a principal machine learning researcher at the Blue River Technology. Jamie Spencer, he was the first person who was leading the first two versions of this monocular depth challenge. Fabio Tossi, Matteo Poggi, Chris Russell, Simon Hatfield, as well as Richard Bowden. This is our organizing team, and everyone's put a lot of effort to putting this together. Today, we'll be hearing from Matteo, Vitor, and Eric about their work and research in the field. The schedule, just to go over the schedule a little bit. So we'll start with the first keynote speaker. So Fatma couldn't make it, so we're having Matteo substitute a substitute for her. Then we'll have the second keynote speaker, Vitor. He's already here. There'll be a 15-minute break after that. Be a good time to talk to people, socialize with the keynote speakers. Then we'll dive into the challenge, the monocular depth estimation challenge results. So Matteo will be running that virtually. Eventually Eric Brockman will be giving his talk at 4:30, and then we'll conclude by around 5:15. With that, let me hand it over to Matteo. Matteo, can you hear me?
Yes, can you hear me? Can you hear me, Ripu?
Give me 1 second. I can hear you. I just connected the audio, so you should be good.
Okay, thank you very much. So I'm going to share my screen. Okay. Can you see my slides?
Sorry,
all looks good.
Okay, so thank you very much, Ripo, for the introduction. Sorry?
Matteo, 1 second. We're still sharing the slide here. Give me 1 second.
Okay.
Matthew, we're good to go.
Sorry, I couldn't hear you.
We are good to go.
Okay, thank you very much. Thank you, Ripo, for the introduction, and hello, everyone. Welcome to our Monocular Depth Estimation Challenge. I will open this workshop with this talk with a provocative title, which is Monocular Depth Estimation, Are We Done? And you will soon figure out why I gave this title to this talk. And here I'm showing you a very quick overview about what we will see during this talk. We will have a very quick introduction about how everything started concerning monocular depth estimation. In particular, we will have a little focus on self-supervised monocular depth estimation, which was the very first topic which ignited the monocular depth estimation challenge that we are that is taking place today. Then we will look at how monocular depth estimation is going on today, and we will have a little focus on more recent works dealing with a fine invariant zero-shot monocular depth estimation, as well as with the very most recent foundational model that you will probably heard about and you will probably see around at CVPR in the next days. And finally, I will show you how monocular depth estimation is still far from being solved. In particular, even the very latest foundation model can still fail in some very challenging conditions. So before starting, just a very quick note and about how it's going on. I will just talk about a fine invariant molecular depth estimation models, but another very hot topic nowadays is zero-shot metric depth estimation, and probably Vitor will give you a look about this during his talk. And then a second disclaimer, unfortunately, this was an emergency talk, so I prepared it very, very quickly, and often I mixed up different color encodings for the depth maps that I will show during the talk. So I'm very sorry for this. So let's start with a very naive definition of what actually is depth, what is a depth map. So let's assume we have any picture like those we have here on the top. And when we want to estimate depth for those pictures, we are actually estimating a new image in which each pixel on this new image contains the actual distance of any point that we have seen in the real image with respect to the camera that collected the original picture. So we will have a new image that we call a depth map, and each pixel encodes this distance. Of course, to have a more pleasant visualization for the human eye, usually we encode these depth maps according to some color scheme. And in this slide, for instance, we are using a color scheme varying from red to blue to encode those pixels that are the closer and the farther from the camera. And what can we do with a depth map? Of course, we can recover the 3D information about the scene that we captured in our picture. So we can take all of the pixels in the single picture. We can use the depth to project them back in the 3D space, thus reverting the image formation process that we carried out when we collected the picture. And we obtain some kind of 3D representation of the scene. In this specific case, we obtained a point cloud by projecting the pixels into 3D points. So let's have a look at how this started. So monocular depth estimation is getting quite long-standing, because I would say we are working on this for more than 10 years. And while at the very beginning, the very first approaches were training some basic convolutional neural network on very few annotated data, I think the very first advance that made this topic explode was the introduction of self-supervised monocular depth estimation. And in particular, in 2016, 2017, we had the very first approach that were capable of learning to estimate depth out of a single input image without any kind of depth annotation on the images themselves. So in this slide, I'm showing you some of the results from one of the very first approaches appearing in 2017. And yeah, I know that looking at these images right now might feel a little disappointing, but I can assure you that for those working on this topic in 2017, these results were unthinkable, because despite being not that accurate, here we can perceive the 3D structure of the scene, and the very surprising point was that everything was learned without any kind of supervision in terms of depth labels. But of course, nowadays the things are very, very different. In particular, through the years, the increasing availability of annotated training data made self-supervised depth estimation going a little in the background in the overall research panorama. And nowadays, one of the most standard approach is to combine as many data sets we have available, of course, with as many ground truth depth annotation or pseudo ground truth depth annotation we have, in order to train the most robust neural network we can. And here in this example, I'm showing the results by depth anything. That is a foundational model that you will see many, many times today during this workshop, and probably also in the next days during the main conference. And as you can notice, of course, the results by depth anything are much, much better with respect to what we could get by means of self-supervision at the very beginning of the monocular depth estimation era. So nowadays we have much, much better results. Nonetheless, even if we have some very strong models like depth anything and a couple more that we will see during this talk, there are still some very challenging conditions in presence of which these accurate models can still fail. Here I'm showing you some pictures taken from the booster benchmark that I will introduce in the reminder. And here we can notice we have some bottles being characterized by some transparent surfaces, both at the top and at the bottom. And what happens if we run depth anything on these images? Well, we can notice how depth anything cannot deal at all with transparent materials. Indeed, we can notice that the bottles tends to disappear in the predicted depth map, meaning that the current model has no knowledge about this kind of objects. Of course, for those of you that are more familiar with the topic, probably you know 4 days ago that Anything V2 came out on arXiv. So today, while I was preparing the talk, I made the prediction, the depth prediction for these images with depth anything, being pretty sure that depth anything V1 was failing. And then I said, okay, let's see how it goes with depth anything V2, because as we will see in a few minutes, this model is even better than the previous one. Nonetheless, we can see that in some cases, the perception of the bottles is slightly improved. Nonetheless, we still have some critical failure cases in which actually the bottle is not perceived at all. So this is just an anticipation for telling you that, no, we are not done with monocular depth estimation. So now we will go a little more in detail into these 3 topics that we will cover with this talk, and we will start by diving a little more into how everything started. So I mentioned 2016 and 2017 as the years during which self-supervised monocular depth estimation appeared and then exploded, making this topic very, very popular. And the rationale behind these kind of approaches is to replace the ground truth depth annotation with some form of self-supervision that we can obtain in alternative manner. And the preferred alternative manner is the use of multiple images. Indeed, as soon as we have multiple images of the same scene, even if we make our neural network process a single image, we can use the remaining images to obtain some self-supervision by exploiting multi-view geometry. And in the literature, we had 2 main families of approaches to deal with this kind of self-supervised framework. The first one was proposed in 2016 by Garg et al. And the choice was to use stereo images in this case. So given a data set in which we have multiple stereo pairs, for each left image in the stereo pairs, we assume it as the input to our monocular depth estimation network. So our network is trained to predict a depth map for this input image or an inverse depth map. And according to this depth map, we retrieve the corresponding right image for the input image. We use image warping according to the estimated depth to reproject the right image over the left image. This means that if our depth map is accurate, we will be capable of reproducing a warped image that will match the left image except near the occlusions. Of course, the more accurate the depth map is, the more precise will be the warped image. And to figure out how accurate is our predicted depth map, we can simply compute the reconstruction error as the difference between this warped image and the original input image. Given this error, then we can simply use this as a form of loss function to make our monocular network learn how to predict depth out of the single image. And the main properties of this framework is, of course, we just need to replace ground truth depth with a second image. And since we are dealing with stereo images for which we assume we actually know the parameters of the stereo camera that we used for collecting them, we are capable of learning a depth map that is in metric scale. The second approach is a little less constrained because it still assumes the availability of multiple images of the same scene, but this time these multiple images are collected by a single camera. So as in this example, we have what we call the target view, which is the image that will be processed by the neural network, and we have some nearby views. So the monocular network will again predict a depth map, and this depth map will be used once again for projecting the nearby views over the target image. In this framework, the main difference is that we don't know the relative position between the images, and we need to estimate that, to estimate such a relative transformation. And for this purpose, we use a parallel neural network that is usually known as the PoseNet to basically process both images together and estimate the relative transformation between the two. Then, using this relative pose and the predicted depth, we can reproject the images and we can obtain the supervision for both the depth network and the pose network. Conversely to what happens when we have stereo images for which we know the exact distance between the two cameras, in this case, we cannot properly estimate the metric distance between the two images. This means that also the predicted depth map will be, by its own nature, up to an unknown scale factor. So in order to retrieve the metric scale for the scene, we will need to actually estimate this kind of scale by means of different strategies. Despite this little drawback, of course, as you might imagine, scaling up monocular videos is much simpler than scaling up stereo images, just because we can possibly collect any video we can source from the web, and any of this video is potentially a source of training data for learning to estimate depth out of a single image. And indeed, James and his team at ICCV last year proposed the Slow TV framework that was basically scaling up the amount of training data, and together with some very nice implementation tricks, they were capable of training a self-supervised monocular depth estimator that is much better than everything that was proposed just before. Of course, even if we are capable of scaling up the data, that is in the deep learning era, what really matters for having an accurate neural network, some weaknesses still remains. Indeed, the self-supervised losses we can get from image reprojection are indeed weaker with respect to the use of explicit depth labels. And a second issue appears when we use monocular videos. Indeed, if we have any independently moving object appearing in this video, these objects will violate the multi-view geometry assumption that are at the basis of the self-supervised losses, and so we won't be able to properly learn the depth for those objects. And yeah, these self-supervised approaches become very, very popular, and this research trend exploded. However, at the very beginning, all of the approaches were focused on very limited datasets. For instance, most of them were focusing only on the Kitty dataset. And this could lead to some biases in the evaluation, and could also limit the advancement in the research on this field. And this is why the very first edition of the Monocular Depth Estimation Challenge was proposed in WACV in 2023 by James and his team. And for this challenge, a new dataset that we will introduce later during the workshop was proposed to as a more varied benchmark with both indoor and outdoor scenes in order to get rid of any bias during the evaluation process. And in the first edition of the Monocular Depth Estimation Challenge, what was quite evident is that self-supervised approaches, despite being to some extent accurate, they were still suffering of several limitations. Indeed, from the depth map that we can see here, we can notice how self-supervised approaches are not really capable of reproducing the fine details that we might have in a scene like this that is taken in a forest. And often they also tend to reproduce the texture from the input image in the predicted depth map as well. So this is how everything started. So we had 3 to 4 years during which self-supervised approaches were the most popular strategies for conducting research on this topic. Then 3 years ago, something changed and a new research direction emerged. In particular, with the increasing availability of datasets and either ground truth or pseudo ground truth depth annotations, some research teams started inquiring about the possibility of mixing up as many datasets as we can in order to train monocular depth estimation model that could be possibly be capable of generalizing on any unseen domain. And this is what the Midas paper did in 2020, and Midas was the very first work following this direction. And in this work, the basic assumption was to train a convolutional neural network to predict a relative depth in a fixed range. For instance, let's say between 0 and 1. And this relative depth was optimized over a varied set of datasets and corresponding ground truth labels, having very different depth distributions, one with respect to the other. And to make this work, the authors proposed to basically learn a depth representation that is invariant up to a scale and a shift factor with respect to the real depth. So basically, the authors admitted that learning metric depth at that time was not sufficient for having a generalizable estimator, and so they proposed to learn this affine invariant depth estimation with Midas. And this made very simple to combining up many datasets. And this way, you know, the more the data you have for training your model, the more generalizable will be your final solution. And yeah, with the advent of Midas and let's say more recent works focusing on this kind of task rather than self-supervised depth estimation, the second edition of the Monocular Depth Estimation Challenge also opened the door to supervised approaches. And indeed, from the results that were presented at CVPR 2023, we figured out that supervised approaches are slightly better at retaining the details that we have in the input image. And of course, given enough training data, they are also more accurate with respect to self-supervised solutions. And nonetheless, Midas basically was followed up by several more approaches until now, until CVPR 2024. And in particular, in the very latest month, we had some very nice works extending this idea of learning an affine invariant depth representation. And some of them basically scaled up this kind of approach to exploit even more data with respect to those that were used by the original Midas. And in particular, in this talk, I will introduce you very quickly, two foundational models that you will see around at CVPR in the next days. And one of these models is known as Marigold. Marigold is a monocular depth estimation framework derived by a latent diffusion model. And specifically, the authors claimed that these very large models that have been trained on billions of images, they will know for sure much stronger priors with respect to anything that we can make them learn on the dataset that we have available for depth estimation. So their idea is we just take an off-the-shelf latent diffusion model. For instance, they took Stable Diffusion V2, and they repurpose the Stable Diffusion V2 model for denoising actually a depth map rather than an image. And so for training this kind of approach, they took the latent encoder from Stable Diffusion V2 and they kept this frozen. At training time, they took the input image and its corresponding ground truth depth map. They extracted the embeddings with the latent diffusion encoder. Then out of the depth embedding, they add some random noise. And then they started the denoising of such a noisy vector conditioned by the image embedding that is provided to the latent diffusion unit concatenated to the noise. So the latent diffusion unit is fine-tuned to denoise such an embedding. And of course, this happens iteratively, as it happens for any latent diffusion model. So at any iteration of the unit, some noise is removed from the latent vector, and this noise is compared with the ground truth noise that we generated, and this difference is used to fine-tune the unit. So this way, we can fine-tune the Stable Diffusion V2 for estimating depth, and at different time, of course, we won't have the ground truth depth. We will have only our single image, but that's enough because we will use the latent encoder to get the guidance for the diffusion process. Then we will sample some random noise and concatenated with the image encoding. Of course, we will proceed the noisy embedding. Once we have denoised this embedding, we will use the Stable Diffusion decoder to obtain the final depth map. And according to this framework, the authors were capable of fine-tuning Stable Diffusion for very few iterations. Indeed, their training was just something like 2 days long, and they used only synthetic datasets for training Marigold. This means they used only a few 100,000 synthetic images, and of course, the importance of synthetic images is that they provide dense ground truth depth that is necessary for making everything work during the latent encoder processing. And here I'm showing you some results just to make you figure out how good the results by Marigold are, and in particular the use of the prior knowledge from Stable Diffusion, as well as the use of perfect ground truth, that is very fine details made available from synthetic datasets, allow Marigold to provide much finer depth maps with respect to everything that was proposed just before Marigold. And this idea has been extended recently by other following up works. Some papers used this idea for estimating both depth and normals, but we won't talk about this today in the interest of time. And another more recent approach used the idea of Marigold to predict depth out of a monocular video sequence. And in particular, the idea was to replace of course, the Stable Diffusion V2 model with a stable video diffusion model, and to fine-tune it over video sequences. And this allows to obtain a depth estimator that is capable of both predicting accurate depth maps as well as temporally consistent depth maps. Indeed, the temporal consistency of the different frames predicted by a monocular depth estimator is usually a concern. But as you can notice in the videos that is playing on the background, this kind of approach that is called chrono depth is capable of predicting depth that remains consistent over time, in particular with respect to Marigold and to the depth anything model that we will introduce in a while. Here on the top, you can see as chrono depth is much more temporally consistent. And of course, yeah, now we talk about depth anything. I've already anticipated this as one of the most popular models coming out in the last months. You have probably heard about this. You will for sure hear more about this, in particular when we will look at the results of this edition of the Monocular Depth Estimation Challenge. And the main idea behind depth anything is to take everything we can in terms of training data to make monocular depth estimation scale up at the best we can. And in particular, the authors were very smart at mixing up a few millions of images with provided depth labels, together with many more millions of images not provided with depth labels. And the main idea is to exploit a teacher-student framework. In particular, a first version of depth anything is trained as the teacher on the few million of images with the provided depth labels. Then once the teacher is trained, a new network, the student starts from scratch, a new training on both the labeled images as well as on the unlabeled images for which the teacher can provide some pseudo ground truth depth labels. And both the networks use an encoder that starts from Dino V2. And during the teacher-student training, the features extracted from the teacher and the student are compared, and a loss constrains the two to remain the same. And according to this strategy, depth anything was capable of generalizing much better with respect to any Midas version and any existing approach pursuing a fine invariant depth estimation. But of course, as I told you, just four days ago, Depth Anything V2 came out, and by the same authors of Depth Anything, and basically they were capable of improving the results even further. And they followed up a similar strategy they already used for Depth Anything, so they scaled up the training data, but this time they learned the lesson from Marigold that was published in parallel with them. So they replaced the training data they were using with Depth Anything V1, which were real images, but having noisy depth labels. And they replaced them with synthetic images having perfect ground truth. So this way, they were capable of training a teacher that is much more robust and capable of predicting much finer details in its own depth maps. And of course, the better the teacher, the better will be the final student that you will have in the end. And just to give you an idea, here there's a comparison between Depth Anything V1 and Depth Anything V2 taken from the paper. You can notice how both depth maps are very good and they can generalize in very different environments. Nonetheless, we can appreciate how Depth Anything V2 is capable of preserving the details much better with respect to the original version. And here there's a comparison between Marigold and Depth Anything V2. And again, we can appreciate how this latter model is more robust with respect to Marigold to some very challenging conditions. For instance, here in the middle row, we have a foggy image in which Marigold to some extent struggle, while Depth Anything V2 is much more robust to this kind of challenging condition. So after these two sections of my talk, you might think, okay, we are done with monocular depth estimation, but as I anticipated you at the very beginning, we are not entirely done. So we can figure out that even these foundational models like Marigold and Depth Anything V2 can still struggle in some very challenging situations. And this very challenging situation often corresponds to some some objects, some elements that belongs to the very long tail of the training data. In particular, all those objects that are non-Lambertian, so that are transparent or that are reflective, may represent a challenge even for the foundational models. From now on, I will refer to this kind of objects as TOM objects, so transparent or mirroring objects. So if I take these two pictures and I process them with depth anything v1, this is what I get. So as we have already seen at the very beginning of the talk, the transparent objects tends to disappear in the predictions just because the monocular depth estimator probably has never seen them in the data distribution. So basically what we need to make a foundational model or any monocular depth estimator be capable of predicting the depth for this kind of objects is just to enrich its own training data. And for this purpose, a couple of years ago, my team and I proposed the booster dataset that is, of course, a benchmark tailored for boosting the research on depth estimation in presence of transparent and mirroring objects. At the very first, the booster dataset was proposed for the stereo matching task, and we collected several scenes, like the one I'm showing here, for which we were capable of providing very accurate DAD maps that could be used as the ground truth. And of course, this ground truth compared to the prediction that we could get with a state-of-the-art stereo networks is very, very different. Indeed, we can easily perceive how the stereo model cannot properly identify the mirror as a planar surface, just because, of course, the reflection in the mirror violates the basic assumption behind the stereo matching task. So what we did was we set up some scenes, I would say something like 60 scenes, in which we had some TOM objects, so both transparent or either transparent or reflective. Then we set up our camera, we collect a set of images with varying illumination condition. And then we started our annotation pipeline. So in order to get the depth for the transparent surfaces, we painted all of the non-Lambertian surfaces, and then we projected some random patterns and collected multiple images over time. Why did we do this? Because by collecting multiple images with some random patterns, we can use space-time stereo to get some accurate depth labels. And in particular, we used the space-time stereo together with a deep neural network to obtain some initial depth labels that were, of course, not perfect, but they were indeed a very strong guidance. Then, starting from this guidance, we had the funny part. We had some manual filtering. In particular, Fabio had a lot of work to clean up all of these depth annotations. And then we had our final dataset. And as we can notice from these point clouds, the annotation we could get are very, very accurate, while what we could get by running a stereo network on the original passive images is something very, very noisy. So with this dataset, we organized a couple of challenges. One took place yesterday at the entire workshop. So just as a reference for future editions, because we are counting to have a new challenge next year. But another challenge is still taking place and will be presented at the Tricky 2024 workshop in ECCV in Milan this autumn. And this challenge is still open, so if any of you is interested into participating and is willing to figure out how to estimate depth on transparent objects, feel free to participate. Here I'm showing you some references, and of course at the end of the talk I will share again these references with you. And I'm going to conclude the talk with some lessons we learned while collecting the booster datasets. Of course, the most important lesson we learned while collecting this dataset is that annotating the non-Lambertian surfaces is extremely time-consuming. In this is a picture just behind the scene when collecting the ground truth for the motorcycle, and here there's Fabio painting his own motorcycle, because this was his motorcycle. And I think this took something like maybe a couple of hours to fully paint the motorcycle. Then, of course, we started collecting the images. We post-processed the images. And in parallel, of course, Fabio was willing to use back again his motorcycle. So he also had to clean everything up. So you can imagine how collecting the ground truth for a single scene is extremely time consuming, and thus this approach is not that simple for scaling up the training data. So having learned this lesson, we started thinking about some possible alternatives. So how can we get some cheaper annotations, some pseudo ground truths with very fewer efforts? In particular, can we do this with possibly any image we could source from the web? So can we download any image with transparent or mirroring objects and obtain some pseudo ground truth from these images? And well, actually, we came out with a simple solution, and the solution was exploiting monocular depth estimations, monocular depth estimators themselves. So we started by studying how the single image depth estimators fail in presence of this kind of image. So here we have a picture in which we have a tiny mirror that is reflecting the content that we can notice here in the image. So if we take this picture and we process it with DPT, this is what we get. So we have this context that is quite large in the image that is influencing DPT, and it's making it believe there is something just behind this kind of object. So since we feel that monocular depth estimation is mostly based on the context in the image, we asked ourselves what happens if we simply take a mask and we simply paint with a constant color the mirror. So we did this, we processed this with DPT, and this is the result we got. So basically, we could get some reasonably good depth map in which we could have a planar surface in place of the mirror. Of course, at testing time, we cannot be there and just paint our image, so we cannot assume this as the final solution, but maybe we can use this to get some pseudo labels for training a monocular depth estimator. And this is how we proposed the depth for Tom at ICCV 2023. So we took a data set with transparent and mirroring objects and some segmentation masks that could be either annotated manually or by some kind of segmentation network. Then for each of the image, we took the mask and we painted the image with some random colors. Then we took an off-the-shelf monocular depth estimation network to estimate some pseudo labels. Of course, since we are using random colors, we might have some ambiguities with respect to the background. So we repeat these multiple times to be sure that at least a few times we are not having ambiguities. And then we predict the depth for any of these images. Then once we have these multiple images, we combine them by means of a simple average or the median of the depth over each pixel. And by repeating this over all the images in our data set, we can produce a training set over which we can fine-tune any single image depth estimator, even the one that we used for creating the pseudo labels themselves. And how do we do this? Well, when we start training, of course, the monocular depth estimator will process the original image over which it will fail. It will predict some kind of depth map, and then we will use the virtual depth labels that we processed before to obtain a loss function and to fine-tune our monocular depth estimator. And here I'm showing you some results. Here we have two pictures from the booster datasets with a very large mirror and transparent bottle. And at the bottom, we have an oven with a very reflective surface. Here in the middle column, we show the results obtained by DPT using the original weights made available by the authors, while on the right, we show the results that we have obtained by fine-tuning DPT on a completely different data set that has been annotated through our depth for Tom pipeline. So once again, the images, of course, were not part of this training dataset. And even if the images that we use for fine-tuning were very, very different, because most of those images were top views on some tables with some transparent objects, nonetheless, those priors from those datasets were enough for fine-tuning the model and make it aware of some larger context for predicting the depth. And these are some references for all of the papers I mentioned during the talk. And thank you very much for your attention. Feel free to ask any question. And I'm sorry if the talk was a little messed up, but yeah, that was a last-minute talk. So I'm sorry about that. Thank you for your attention. Ripu, can you hear us?
Matthew, can you hear us?
Yeah, I can.
Okay. Yep.
So can you use the technique that you went over to do?
Oh, wait a second, I can't hear you anymore. Maybe my... Oh, wait a
Metric
second,
depth
I can't hear you anymore.
estimation.
Maybe my PC has some issues. Okay, try again.
Can you hear us?
Okay, now I can hear you. Yeah.
So the question is, can you use the techniques that you shared for metric depth estimation?
Okay, actually, you mean which technique? The last one or any of those techniques that we mentioned before?
Just in general.
Just in general, any of
Just
those
in general,
techniques.
okay. Let's say I focus mostly on techniques estimating relative depth. This means that the network itself is not targeting metric depth as the final prediction. But of course, you could fine-tune all of these models for predicting metric depth. Indeed, something I didn't mention in the interest of time is that sorry, I'm going just back. Depth Anything V2 made an experiment like this. So they first train a relative depth estimator, and they also fine-tuned it for metric depth estimation. While there exists also an entire new research trend that concern directly predicting metric depth. And there's a couple of works at CVPR, and I think also probably Vitor will talk about one of his work on metric depth estimation. So usually we have these two different approaches, but in principle, you could fine-tune all of these also for metric depth.
So for the depth of the method that you showed to actually detect depth in the reflective surfaces. So for training, did you actually like on the image create the mask manually and then like train that network as it is? And then that's why the depth was estimated correctly for those reflective surfaces?
Matthew, I'll just repeat the question. So the question is depth for Tom. In that data set, did you manually create all the masks?
Okay, actually we did both. We tried both with manual annotations because the dataset we used for training was providing the segmentation masks, which were of course accurate. But we also tried with the prediction by a segmentation network. Indeed, there are a couple of works. I can't remember the name. Maybe one was Transp to Seg, something like this, in which the authors were training a segmentation model for identifying the transparent and mirroring surfaces. So of course, in principle, you could have a neural network predicting the mask for you. Of course, this mask will be likely to be less accurate than those that you can annotate yourself. But in our paper, we showed that the results are almost comparable.
And any change in the the field of view, like right now you showed images are close to the camera, but what if the field of view is larger? If there's like a reflective mirror at the back end and while you're seeing the indoor scene, would that when you train the network, would that account for the view change as well?
So
What I'm
Matt,
asking is because like even for the video scene where somebody's taking a camera, scanning the room, like you can start from small distance and then you can move back farther and then scan the room. So in that kind of like a streaming scenario, how would would you foresee any issues with this method?
Matthew, do you want me to repeat the question or you got it?
Yeah, because it's we can't hear very well from Zoom, or actually I can't.
Cool. So the question is that when you change the field of view, so for example, you're taking a video of a scene and there's a mirror in the center of the scene, but you go backwards. So the field of view changes and therefore there's like a lot more context in the scene. And the reflective mirror becomes a small part of the scene rather than the whole scene, which is there in the depth for Tom dataset. What happens in that case?
Well, actually, I don't know, because in the dataset we used, let's say the mirrors were covering a large part of the pictures. But yeah, I would assume, I think the depth anything V2 paper showed, I can't tell for sure, but I think at some point they have a qualitative example that was something like this. They have something like a truck that on his back was showing what was in front of the truck. So basically you had this truck showing you the car in front of the truck itself. And the basic monocular depth estimators were actually predicting a hole in the truck, because even if the context is not that small,
Cool. We may
maybe it
have
is
time
sufficient.
for one more question.
If I have a stereo, if I have a stereo rig, does it ever make any sense for me to use binocular depth, or should I always just use a deep stereo method to predict depth of the set?
So Matthew, the question is, if I have a stereo rig, does it make sense to use monocular depth estimation or should I go for deep stereo methods?
Okay, yeah. From my personal perspective, I think you still should go with the stereo, because of course with stereo you have metric depth if you know the parameters of your camera, and of course it's a matching problem. So with the very latest state-of-the-art models, I think you should go for stereo. I don't know how long this will last, because with depth anything V2, we are getting better and better. So probably at some point, there will be some use case in which stereo probably won't be that convenient with respect to this kind of foundation models.
All right. Thank you, Matthew. We'll move on to our next keynote speaker.
Thank you very much.
Sarah. Right, so our next speaker is Victor Guizili, Altos, California. His interests include self-supervised learning, monocular depth estimation, unsupervised domain adaptation, implicit visual representation, camera calibration, and vision-based machine learning in general. He has close to 100 publications in this related area, in addition to the large number of patents in different stages of filing and applications in various products. He is the creator and currently maintains the PacketNet SFM and WIDAR repositories, two of the most widely used depth estimation code bases in the scientific community. He co-organized the first 3 editions of Frontiers for Monocular 3D Depth Perception workshop and has also given several talks in the top tier conferences. So welcome, Victor.
Thank you. Share.
Zoom. Video connect Zoom.
Connected, but I don't know. It's here. Not really.
Let's get open.
Okay, there you go. Oh, you just,
We can see it.
can you see?
Yeah. Uh,
Can you hear me? Can you hear me on Zoom?
Yes, I think there's a little of echo.
Yeah. Sorry for this technical difficulty. Yes, so thank you for the introduction and thank you all for coming to this wonderful workshop. My name is Vitor. I'm a staff research scientist at the Toyota Research Institute. And this is the name of my talk for today, an ode to modal depths. So for those who don't know, an ode is a type of poem used for celebration to elevate a person or an idea. And this is what I'm planning to do here today. I've been at TRI for the better part of 5 years already. And during this time, my research has always been centered around depth estimation in one way or another, and other geometric-based tasks, as we like to say. So 5 years is a lot of time. There were lots of publications, lots of patents, and I had the pleasure to see the field evolving, just as Matteo just was talking about now, and with all challenges being conquered, as they always do, and new ones rising up to take their place. So, and by no means I was the only one. There were many other brave people taking up arms to face those challenges, sometimes finding solutions that I could never have thought of, and sometimes making me wonder how the paper got accepted. So today I'll talk about my journey, how I started, how I got to where I am today, my decisions along the way, that were kind of shaping the field, but also being shaped by the field that it was evolving, and what I think will happen next. So hopefully you find this useful, see a little bit of your own journey, or get inspired to go on your own adventure. And thus, for my first verse, I'll start with PACnet. So it was a Norway CVPR 2020, and it touched upon a very interesting aspect that is unique to these geometry-based tasks, which is self-supervised learning. So I'll briefly touch upon that, even though Matteo did a pretty good job on his talk previously. Most people are familiar with self-supervision in the sense of mascot encoders, contrastive learning, and so forth. But here there are some additional priors that we can use to train an actual depth network without ground truth of any kind, just a sequence of images, usually videos, but I'll expand on that later. If you have two such images, you can run one of them through your depth network and unproject the information to a 3D point clouds. Another network estimates their relative transformations across the two images, and you can use to warp the 3D point cloud from one frame of reference to the other frame of reference before projecting back to produce a synthesized version of the first image, of the second image, using only information from the first image. And that's your training loss. Given some assumptions, this loss will be minimized if and only if your depth imposed networks are correct. That's how you train a depth network without any labels. And because our training objective is photometric, it's easy to see that resolution plays a big role. The more detailed your image is, the more accurate your reprojection has to be in order to minimize the photometric error. But back in the day, and even by today's standards, honestly, processing high resolution images is very time consuming, taking up a lot of time and memory as well. So our main contribution here was a novel architecture designed to preserve spatial information during the encoding and decoding stages. So instead of downsampling using max pooling and upsampling with bilinear interpolation, we propose packing and unpacking operations that use 3D convolutions to switch between spatial and channel dimensions. So they are preserved all the way from the beginning to the end. As expected, this network was much larger than what was available at the time, reaching upwards of 128 million parameters, which was quite a lot back in the day. So times indeed change. But we showed the PACnet scales better than other networks relative to the number of parameters, that it benefits more from higher resolution input images, and also scales better with range, with the gap in performance increasing as we consider longer distances, which is expected since preserving high resolution details is even more important as we consider regions further away, where one single pixel can cover an area of several meters. So you indeed need fine-grained details on those cases. So a little bit into the metric realm that I was going to talk a little today. Another contribution of this paper is weak velocity supervision. So one key problem, as we all know, with self-supervised learning is scale ambiguity. meaning that the predicted depth and angle motion will not be metrically accurate. It's going to be up to scale. Makes sense, since there is no way to disambiguate between the size of objects purely from images. So are you driving through a city or through a toy model of a city? Everything's correct up to scale. So to address this issue, we show that it's possible to inject metric information into the pose network by supervising the estimated translation with instantaneous velocity measurements. And in doing so, the depth network also becomes metric, because it needs to be consistent with the pose estimate, with the pose estimates, because everything is learned jointly. And as you see, this metric monocular depth estimation idea will become a recurrent part of our research direction at PRI, and is currently a very hot topic, as I'm sure you're all very aware of. So we've been doing work on this, but it took us a while to get there, and took the field a while to get there as well. Our third and final contribution was a new data set called DDAT, or DDAD, as some people like to say. It was collected with Toyota's vehicle fleets covering US and Japan cities, and is actually a very, very small snapshot of our own internal data sets that we use to train our models internally as they make their way to deployment and production. It contains 6 synchronized cameras and high-density ground truth LiDAR with ranges up to 250 meters. And it enables us to explore also cross-camera consistency, as I'll talk about later. And also over the years, it made its way to become one of the standard benchmarks for depth estimation, which is very nice to see. Here are some PackNet results on the DDAT data sets. Those were pretty amazing back in the day. So it's purely self-supervised and scale aware. So these are actually metric because we have the velocity measurements. And it was pretty amazing back in the day. I still find it quite amazing, and gave us the indication that this was a very good direction to keep pursuing. So what to do next? The way I like to see that we started from the hardest problem, which is learning from unlabeled videos. Turns out it wasn't the hardest problem by far, as I'll talk about in a bit. But the idea here is, how do we have a stable way to solve a problem without any supervision? What if you had some labels, even if not the ones that you are looking for? Weak velocity supervision was a step towards that. And in this follow-up paper, we explore semantic segmentation as another alternative. So still no ground truth. Those are generated from a frozen semantic network. And the key idea here is to use the features from the semantic network to guide the generation of better depth features. So you are adding information that is not available in the image itself because it's semantic. So it had to come from somewhere else. To achieve that, we use pixel adaptive convolutions to generate semantically guided kernels for the convolutions operations of the depth network. So they have more information in addition to the raw pixel colors. And by supervising the network at a feature level, you preserve this information every step of the way, just like we did for the packing and unpacking operations from the previous paper, and leading to better results than just providing the semantic, the predicted semantic map at the input level. And plus, you get to run those two networks in parallel because the semantic network is frozen and never changed, so you still get that. And you can run both in parallel, which is quite useful for real-time applications. So there is no latency. And another key limitation of self-supervised learning we address in this paper is what I like to call the infinite depth problem. If you have an object moving at the same speed as the camera, there will be no relative motion. So your network will learn, there will be no relative motion. And that's what you expect to learn from something that is infinitely far away. So there is no motion if you're infinitely far away. So your network will learn to map those objects to very large depth values, creating these object-shaped holes in your depth map at the end, which is kind of dangerous if you are applying that to something that is practical and try to avoid obstacles. So our solution here was a two-stage training procedure. First, to train a model using all the available data and accept that we have this problem. So that's the first row. Then you use this model to filter out any problematic frames by detecting the estimated 3D points that fall below the ground plane. So why is that? So if you have an object on the ground that is very far away and shouldn't be, its point cloud will go through the ground. You can see that with some geometry. And that can be automatically detected by just finding pixels that fall below the main ground plane assumption. And then you remove these pixels, and you remove the frames that contain those failure cases, and then you train a second model. And just like Mateo was saying, if the model was not was not exposed to these sorts of failures, it will not learn those failures like he did for the mirrors. If you remove the mirrors in your training data set, you will not learn how mirrors behave. So you go through whatever else is available in your training data set. And the infinite depth problem kind of goes away just by treating the infinite depth as a bias problem in your data sets and de-biasing your data sets to be more realistic. Moving on to the next one. Another sort of source of supervision we explore in this other paper was depth itself. So how sparse you can go while still extracting useful information to improve self-supervised learning. And of course, we produce metric estimates. So this is semi-supervised learning because we're doing self-supervision and supervision jointly with increasingly sparse depth maps as the supervision. So the goal here was to produce a supervised objective that is more aligned with the photometric self-supervised loss that we use, that operates by warp information across frames and at a pixel level. So we created a supervised loss that also operates at pixel level by reprojecting the supervised error onto the context image. So instead of warping the pixels, we warp the range error between prediction and ground truth and minimize that as well, jointly with the photometric error. So there is a pixel level and there is a range error level of losses, but they both work at the image plane. We experimented with various levels of sparsity in our data sets, ranging from full supervision, around 20,000 pixels, to less than 100. And our proposed reprojected distance loss consistently outperformed the other traditional supervised losses, especially at lower density settings. And now, taking one step further, what we tried to do next was investigate what happens if you actually have depth labels at test time. So this is a slightly different problem than monocular depth estimation, which try to predict a depth map, and that's why I call it depth completion, because we're trying to go from a sparse depth map to a dense depth map with the help of your image. Here we propose a novel module called SAN, so sparse auxiliary networks, that uses sparse convolutions to process the input depth maps that you have available and injects the information into the skip connections of a traditional monocular depth estimation that does prediction. One very interesting benefit of that is that you can turn the same module on and off. So if you don't have any input depth, you can use this network for prediction. But if you do, you can just turn it on and switch to depth completion and getting all the benefits that come from this additional source of inputs. On this plot here, you can see the effects of different amounts of sparse depth data during training. As few as 1% is already good enough to see improvements, and you can see that depth completion improves by quite a lot as you provide more input depth data during training and during evaluation as well. But the surprising thing here is that we also observe improvements in depth prediction, showing that this joint training leads to improvements even if you don't have input depth at test time. So essentially, we get these improvements for free by just changing how we do training to leverage input depth as an input as well, rather than just as a source of supervision from our network. Plus, you can get the benefit of turning this on and off in case you have this information available. Another very important aspect of monocular depth estimation that we studied and we are still studying, I think this is a very exciting topic, is its use as a pre-training tool, so to serve as a feature extractor for downstream tasks. Self-supervision gives you depth for free, but even ground truth depth maps are much easier to obtain when compared to labels for some other tasks, such as semantic segmentation or 3D object detection in this case. So what we did was modify a monocular depth estimation network, a monocular 3D detection network, to include the depth estimation heads that share as many parameters as possible with the other outputs, in this case, the confidence heads and the 3D bounding box heads. We then pre-train this network using different amounts of depth data from our larger DDAT internal data sets. I think we end up towards of 15 million samples in this case. And as you can see on the right, pre-training of more depth data consistently increased 3D detection performance, even though we are still fine-tuning on the same amount of 3D bounding box data, which is much harder to label than depth data in this case. Unfortunately, we could not release this data set, but we did release the pre-trained DD3D backbone from this paper, and for a while, pretty much all of the leaderboard methods were using our backbone, which was pretty cool to see as well. So in our follow-up work presented at ICRO last year, we show that self-supervision can also serve as a pre-training tool for downstream tasks. So leading to improvements over our original DD3D backbone across the board by injecting even more unlabeled data, which is even easier to obtain than labeled data in this case. So now there is no limit to how much data you can use to improve the downstream task. And now that we show that depth estimation can be used to improve downstream tasks, the next one to explore was semantic segmentation. So now not as additional inputs, but as the outputs. But instead of pre-training, we focus on unsupervised domain adaptation, where the goal is to improve performance of semantic segmentation of target domain without having access to any labels from that domain. That sounds very similar to what we're doing for self-supervised learning, where the whole point is to train without labels. So what we did was multitask learning with a single encoder that takes as inputs an image and two decoders, one for depth and one for semantic segmentation. For training, we had a combination of synthetic data, where labels are fully available, they always are, and real-world data with only videos. Considering a mixed batch from these two domains, for synthetic data, we supervise for depth and semantics, so because it was there, and for real-world data, we only self-supervise for depth on the videos. That's all we could do. So there's no way to self-supervise semantics without any other assumptions. So because there was only one encoder, the self-supervised domain adaptation from a depth perspective actually led to improvements on unsupervised domain adaptation for semantic segmentation, even though we never actually trained on this task at all. So the geometric priors in self-supervised learning for depth estimation were being used to improve a task that had nothing to do with geometry. Everything was happening at a feature level, like we did for PackNets and like we did for the semantically guided work as well. So that's a very interesting aspect, is what are you learning at a feature level for depth estimation. So that was like the underlying strategy that we're going for here. As a result, we achieve state-of-the-art performance without any bells and whistles, no pseudo-labeling, self-training, only multitask self-supervision. So this is the semantically mapped point clouds from the same network just run for both tasks simultaneously. And as I discussed before, the introduction of semantic segmentation, semantic information during training also led to improvements for depth estimation with sharper and more temporally consistent frames. Again, because we have this additional source of information at a feature level. So now for our next paper, a little bit away from mono depth, but still depth, we address a very common question in self-supervised depth estimation as well. If you're training with multiple images, why don't you use multiple frames at test time as well? So this is a very good question. And to put it simply, back to what Matteo was saying as well, self-supervision is not perfect. It relies on some assumptions that most of the time just are not true. Real-world environments are almost never fully static. You have non-Lagrangian surfaces. Different viewpoints will lead to changes in brightness, occlusions, textureless areas, and so forth. So when training, those failure cases tend to average over time, and you can still expect your model to have enough correct information to properly learn. And even then, there are some failure cases like the infinite depth problem that I was talking about earlier. But during inference, those failure cases tend to be catastrophic when the model needs to rely on a proper pixel correlation across images. So that's also a potential shortcoming from using stereo, as someone was asking in the audience. So our solution was to improve the feature matching. So we have a novel feature matching module. So for each target, that uses attention values as a proxy to match candidates. So that was perhaps our first foray into transformers. For each target pixel on your target image over there on the left, you discretize the viewing ray across different depth values, and you project those 3D points onto the context frame to generate a series of matching candidates to produce a cost volume, in other words. And features from this target pixel, image features, are cross-attended with each one of those potential candidates, followed by self-attention between the candidates themselves. We do this several times, and the resulting attention values are used to select the most probable match. And that's how we're going to do the correlation that leads you to the depth that we're looking for. Here's a very interesting plot, kind of hard to explain, but I'll try. So what you're seeing here is a cost volume between two frames containing the matching probabilities. On the right, the metric that we're seeing is image similarity, SSIM. And on the right, you have our feature matching module. As you can see, our probabilities are much sharper, with peaks only around the actual true value, while the SSIM has a very spread out distribution. You can see that on the bottom plots, the blue lines show our SSIM, shows the SSIM probabilities, the blue lines. The red lines show our matching probabilities, and the dots show the actual ground truth value. Visually, it's very hard to see where the blue lines peak, but it's very, very clear from our matching module. So that's why on the top, you can actually see with your own eyes the predicted point cloud from the cost volume itself, while the SSIM cost volume is very blurry and you need some heavy post-processing in order to extract something useful from that. Putting all of this together, we're able to improve upon single frame self-supervised depth by leveraging multi-frames at test time as well, even in dynamic and outdoor scenes. It's worth noting that we're still learning the poses jointly. So the epipolar reprojection to produce the matching candidates is a free variable that is being optimized alongside everything else. So this is still a joint learning problem. So now, remember when I said that we had started from the hardest problem, which was learning from unlabeled videos? Turns out that was not completely true, since there is a hidden label that we've been relying on this whole time, which is the camera model. Without it, you cannot unproject your depth map to a 3D point cloud, and you cannot project the war point cloud back to the context image to produce the synthesized image for the photometric loss. So if you truly want to train on unlabeled data from any source, you should be able to use data sets where this information is not available. So YouTube videos or whatever source you care about. And you should be able to, and I think more importantly, you should be able to use data sets that are not pinhole data sets that have distorted and all sorts of strange geometries, because that's data that's available, should be used in principle. So here, our solution was to predict the ray surface alongside with the depth estimate. So we are learning depth, pose, and ray surfaces, which are essentially pixelized viewing rays pointing from the center of the camera to the direction where that 3D point actually is in space. So the unprojection operation is trivial. Just multiply your predicted viewing ray with the predicted depth. But the unprojection operation is not so trivial, because now there is no way to know where each 3D point is going to fall in your image plane for the grid sampling. To address this, we propose a cosine similarity-based projection operation that compares the vector generated by a pinhole projection to all viewing rays in a patch around that point. So we do patches for efficiency purposes here. And the closest vector, according to this cosine similarity, will be the one most likely to be pointing to that 3D point. So that's where the projected point will fall on the image plane. And then you can do the grid sampling, and then you can pay the loss, and everything works out just fine. As you can see, this is a very, very over-parameterized solution. But even so, we managed to train depth, eagle motion, and ray surfaces jointly with very different camera geometries. So here are some examples of predicted ray surface using p-hole and catadioptic models, omnidirectional models. The model in the training protocol is exactly the same, just providing different data, and that leads to very different camera geometries, while still leading to accurate depth and eagle motion, regardless. Here are some examples of our 3D point clouds reconstructed in very distorted settings. The one on the right, actually, I'm a huge fan of this video. It shows that our model works underwater, which is a very distorted domain. Even worse, this distortion changes at a frame-to-frame basis, since the water is constantly flowing, so everything changes all the time. I don't think any single camera model will be able to handle this data set long-term, because the calibration parameters change every time. But because we produce viewing rays and ray surfaces for every frame, it's a frame-specific calibration tool. We can successfully process this data set along the way and still produce accurate depth and eagle motion estimates. So this is accumulated over time, and you see that things really fall nicely throughout the entire run. Sure. Our near ray surface approach worked and gave us some amazing results, but there were still several drawbacks. Inference was fast, but training was quite slow because the projection operation had no closed form solution. So we had to calculate this whole similarity every time, which was quite demanding. And the over parameterization also led to some instability in our training. So we set up to find a more practical solution. And here on this paper from Micro 2022, we show that the unified camera model can also work as a very simple alternative to a wide range of camera geometries. So we had a closed form solution and could approximate any central camera with a single additional alpha parameter. It works by first projecting the 3D point onto a sphere, offset by alpha, and then projecting this onto the image plane using an actual pinhole model. So it's a pinhole plus alpha that gives you this wide range of camera geometries. So by using this camera model, we are able to train on all sorts of non-pinhole data sets and even across multiple data sets with independent camera geometries by learning a different model for each and still sharing the depth and pose networks. So we just switched the camera model and we're still learning one camera model for each data set. So, and also it serves as a self-calibration tool because our goal is not to produce pixel level ray surfaces now. We are actually producing a compact camera model that can be deployed or compared to traditional target-based tools. We actually showed that our methods was able to achieve sub-pixel accuracy compared to these tools just by training on videos. So no need to go around with your calibration checkerboard and calibrate your camera every few hours or so. And again, these are some in the wild results from a cyclist with a GoPro camera and from a robot navigating a supermarket. On the second one, you can see the poses are actually very accurate as well. And the point clouds as well. They still produce like straight walls, even though the input image is very distorted. So we are bypassing the distortion and producing real 3D point clouds that match in space. So now that we got intrinsics out of the way, the next target we set up to solve was extrinsics. Up to this point, we've been using only temporal contexts for self-supervision. As usual, we have video. But if you have a data set with multiple cameras with some overlap between those cameras, it's also possible to self-supervise using spatial contexts by taking two cameras from the same time step and warp information between them. So that's called generalized stereo case, because you have cameras that could be anywhere, but you know their relative transformation, so you can warp information. And even better, as I show in this paper, you can use different cameras from different time steps in what we call spatial temporal contexts. As we show here, this approach leads to pairs of frames with more shared information, since now we can combine frames across space and time to increase the amount of overlap. You can see that on the right image over there. Temporal context has a lot of overlap, as it should have. The camera is not moving that much. Spatial temporal has way less overlap because mostly focus on the left and right portions of the image. And with spatial temporal context, you can pretty much double the amount of overlap that you have and also increase the amount of information that you have for standard tricks, such as auto-masking and minimum reprojected error. That's why the photometric law is actually dimmer there, because you have less errors that you can use to produce a better proxy for your self-supervision. We're still producing a single eagle motion estimation since the camera rig is assumed to be static. And because we know the extrinsics, we can propagate this estimate across all the other cameras, so everything is moving jointly. And even better, because the extrinsics are metric, we can propagate this information to the depth network and to the pose networks doing training. So everything is still scale aware. So that's similar to the weak velocity supervision, but less restrictive, because now you don't need constant measurements for velocity. You just need a pair of cross-calibrated cameras. On the left, those are depth maps from all 6 cameras of DDADs. And you can see how well they overlap without any sort of post-processing, which makes sense because now they have one single scale that is shared across all cameras, the metric scale, rather than each camera converging to its own arbitrary scale, as I'm showing you the top right there. So there is no way they are going to converge to the same thing because they are not constrained by anything. The extrinsics constrains them. There are many follow-ups building on top of our full surround monodepth. And our own follow-up work presented IROS last year, we focus on removing the need for calibrated extrinsics as well. So trying to remove that constraint again. We propose a multi-stage training pipeline, starting with the standard temporal monodepth model that is shared across all cameras, but each one is treated individually. We then freeze this model and use it to estimate cross-camera rotation, and then the full extrinsics. And then we optimize everything jointly to further fine-tune results. Plus, if you still want metric estimates, you can inject velocity supervision as before, or provide a true extrinsics for any single camera pair, so that the metric information is available to flow to all the different predictions that we care about here. So we can still now have several ways of providing metric for our model. Here are some results compared to COMAP in easy sequences where the environment is static with reasonable motion. We are comparable with it in DDAT sequences and KD sequences. However, in more challenging cases with lots of dynamic objects or very high and low speeds, we exhibit a lot fewer failure cases, and we outperform COMAP by a large margin overall. And you can see the cameras being optimized on the video to the right over there. In another spiritual follow-up to this work that just hit archive a couple of weeks ago, we look into self-supervised depth and ego motion estimation as a source of geometric priors for bundle adjustments. We focus on droid SLAM and as our baseline and investigated some of its failure cases, showing that they are very similar to what we observed in our previous paper. So dynamic environments, sequences of very high or low speeds. So that was droid SLAM and other SLAM-based methods were not really working well in that setting. So what we did, we kept the SLAM model frozen and you train a self-supervised module aiming at refining the optical flow that were being used as input to the bundle adjustment procedure. So improving the optical flow by using the same procedure that we've been using for self-supervised depth and ego motion. So that's a different way of optimizing the same problem. And turns out this was enough to greatly reduce failure cases and improve performance overall without ever having to fine-tune the SLAM model itself, just by improving what it takes as inputs by leveraging self-supervision again. And now, speaking of optical flow, one issue with self-supervision that I mentioned a lot is its inability to deal with dynamic objects. Makes sense if you only have depth and ego motion predictions. There is no way a 3D point will move in time before it's reprojected onto the context frame. So it doesn't account for external motion. And a straightforward solution would be to estimate scene flow as well. So there is one additional 3D vector that moves each point in 3D before it's reprojected. But self-supervising depth and scene flow jointly in a monocular setting is an even more U-pose problem, because now there are infinite combinations for any points to fall anywhere, and there is no way to constrain this problem. So in this paper, we explore a similar setting as our supervised domain adaptation work, and now we can use self-supervised depth estimation to transfer information across domains, one synthetic with full supervision, and one unlabeled, where only depth self-supervision is available. Following rafts, we start by estimating features from each image and building a correlation pyramids that allows us to match pixels across frames. And we sequentially estimated the optical flow by querying from these correlation pyramids. At each iteration, we use the previous estimate to warp pixels across images, just by adding the optical flow in this case, and find the closest match around that area. Once you have your final optical flow estimates, you can triangulate it to produce an initial depth map, which will have a lot of failures, just like I said in our multi-frame work, because it doesn't take into account any dynamic objects and doesn't take into account any of the standard failure cases of self-supervision, but that's good enough as a starting point. And now we encode this depth map and combine it with different image features and start a second round of iterative refinements. But this time the warping doesn't happen with optical flow. It's done with depth and scene flow. We unproject the estimated depth, we add the estimated scene flow, and project back to find the closest match around that area. And a key point here is that we start from the estimated optical flow from the previous rounds and keep refining, just now with a different warping procedure. So we don't lose what was done in the optical flow rounds, just keep refining it, but now adding these additional tasks that we're trying to learn. This approach, combined with sim-to-real and supervised domain adaptation, enables us to, as far as I know, be the first ones to successfully self-supervise depth and scene flow jointly in a monocular setting, and kind of get rid of the inability to deal with dynamic objects. So now off on a little tangent, this is a very interesting side project that we explore along the way. In all of our monocular depth estimation applications so far, we focus on outdoor scenes or indoor room level environments. And on this paper, we focus on a very different setting. What if you only have an image from inside a tactile sensor with a range of just a few millimeters? These sensors, they aim to estimate physical properties of such as force, pressure, object shapes based on the deformation generated when they touch something. In this case, we had a range sensor inside the bubble to detect this deformation, and the goal is to replace the range sensor with a monocular depth network. If it works, we would be able to remove the range sensor and bring down overall costs and dimensions, which was quite appealing for us. And turns out it worked quite well in this setting. Here are some examples of input images, ground truth depth maps, and predicted depth maps. As you can see, the images are not very expressive. It's only a grayscale camera pointing at a dotted pattern. But even so, we are able to accurately approximate the range sensor and remove the need for a whole additional sensor in the tactile bubble that we're using for our robots internally. And I think we have a few papers on that as well. And on the right, you can see the profile created by the point clouds, the estimated point clouds, and the align object there for shape and pose estimation. So that's another success of monodepth in a setting that I don't think anybody had explored before. So, and finally, getting to more recent times, in this new line of work that we've been exploring over the past couple of years, the goal is to look into implicit representations for depth estimation. So far, I talked about explicit representations where one image goes in and a depth map comes out. So with a one-to-one mapping. Any sort of geometric priors or constraints will have to be applied at some stage, either at the loss level, so self-supervision, domain adaptation, and so forth, or at the architecture level, so cost volumes, epipolar projections, and such. And the model will struggle if any of those are not true, they do not hold. In the representation that we're exploring here, the goal is to learn implicit geometry without any baked-in assumptions. So we provide the geometric information at an input level combined with image information, using, in this case, a perceived I/O style architecture. This information is cross-attended with a learned latent representation, and further processed with self-attention to produce a conditioned latent representation. What this means is that it combines the global information from the latent representation, and that is shared across all data points and stores the priors that we're trying to learn, with the local information from each specific scene that gives context to these global priors. When this is done, you can decode from this condition representation using only geometric information that tells you from which viewpoints we want to extract predictions, in this case, depth maps. This is not volumetric. This is a single query that gives you the pixel prediction. So it's a depth field network. That's how I call it define, depth field network. Another important contribution of this paper was some data augmentation techniques designed to essentially make the problem harder, but still geometrically consistent. So the network has to learn the proper geometric priors instead of just overfitting and finding shortcuts that don't lead to any meaningful priors being learned, which happens a lot with transformer architectures. So those two are virtual camera augmentation that creates new viewpoints. So we have this point cloud available from the available viewpoints. We can project those to novel cameras located anywhere in the scene, and creates sparse depth maps and sparse images corresponding to that location. And they will be sparse, but we don't really care about that because we only care about a geometry during decoding. So we can just throw away any invalid pixels. The second one is canonical jittering to approximate equivariance in our latent representation. So if the entire setup is translated or if it's rotated, the resulting prediction should be the same. So back then we couldn't enforce that in any way other than at data level. And that actually helped results with quite a lot. And as a result, other than state-of-the-art performance in generalized stereo and video depth estimation, we have now this geometrically consistent latent space that we can decode from any viewpoint. including from outside of the encoder cameras, as I'm showing here. So the red camera is virtual and can be moved around. This is real time, by the way, so it's actually a very fast network. And on the bottom left, you can see the available point clouds explicitly projected to that new viewpoint and the render depth map. It does a very good job both interpolating and extrapolating from the available views. So this is all due to the geometric priors that are learned and can be transferred to scene-specific tests. So not going to get into details. This paper still hasn't hit archive yet, so I cannot really talk that much. But we've been doing some follow-up work to extend the perceived error architecture to be actually equivariant. So we're not approximating anymore with data augmentation. We are enforcing by design that it should be equivariant. In broad terms, we use spherical harmonics to encode camera information and go from these equivariant embeddings to an invariant latent space. And from there, you can use standard decoders to produce exactly the same outputs when translating and rotating the entire visual setup, as well as in switching between canonical cameras in your views. So hopefully, anytime now, you'll be able to read more about it. So how I'm doing on time?
We have about 8 more minutes.
Okay, that should be fine.
Time for questions.
Yes, yes. I'm almost done. So in this official follow-up to define, so already published and everything, we explore ways to remove the need for depth supervision and come back to the self-supervised setting. And what we came up with was the joint training of multiple solutions to the same problem. So one volumetric, a radiance field that we sample and composite, and one single query with specific depth and light fields. So they're all decoded from the same representation using different heads, and that's why the name Delira. So depth, light, and radiance fields. There are two main contributions here. The first one, we use multi-frame self-supervision in addition to the standard single-frame novel view synthesis loss. Because we have multiple images, it seemed like a waste to not leverage this multi-view consistency. And that's something most NERF papers weren't doing back then. I don't think anyone was doing that back then. And this was quite useful as a way to regularize your learned geometry in the field view setting. So addressing the shape radiance ambiguity problem. So now NERF doesn't have a way to cheat and produce very high quality images without the proper underlying geometry. And the second one was ways to synergize between those two representations. So volumetric renderings are used to produce virtual views for single query data augmentation, like we did for define, but now without the need for supervised depth. So we have this implicit structure that we can decode, produce the ground truth depth, the data augmented depth maps, and use that to supervise our single query. And at the same time, we can use the single query depth, decode the single query depth to improve importance sampling for volumetric rendering. So we can refine it by only querying from point clouds around these initial estimates. Putting these contributions together, we are able to achieve state-of-the-art field view novel view synthesis, outperforming other methods that rely on sparse depth supervision and even priors from pre-trained networks. So this has no additional networks, no additional priors. Everything is learned from 3, 4, 5 images from a scene, and that gives you pretty useful 3D reconstructions. And yeah, and you also greatly improved volumetric rendering because now we can sample way fewer points because we have this initial estimate from the single query depth head. So the previous works focus on multi-view, implicit multi-view geometry. And now here on this third work, we go back to the monocular setting and explore another very important geometric prior, which is scale priors. As we all know by now, monocular depth estimation is ill-posed because there is no way to infer scale from a single image. So if you're supervising, you can introduce metric via your label data that you use to train, and you explore several other ways. So velocity, extrinsic, sim to real, etc. But even if you get metric depth for data sets, it will most likely not transfer to other data sets because the camera model is different, which changes the underlying projective geometry. So there is not just an appearance domain gap in this case, there is also a geometric domain gap that we need to overcome before we can truly zero-shot transfer metric depth across domains. So in this work, we propose to use our input level geometric embeddings to introduce information about the camera model to the network, in addition to the image information, and let it learn global scale priors, and those can be zero-shot transfer across data sets. And that's why I call it zero depth. That was our first network that focused on zero-shot metric depth estimation. As you can see here, the pipeline is very similar to what we had before, with one main difference: the variational space is the latent space is variational. That means that it's storing an actual distribution. Each weight is broken into two values, one for mean and one for standard deviation. And once it's conditioned, you can sample from this distribution and decode from this sample latent space, generating a depth map or any other task that you might care about. This allows us to achieve state-of-the-art results on zero-shot metric depth estimation, outperforming other methods that start to pop up at the same time. Here are some reconstructed point clouds alongside the ground truth with the little points heights colored, so we can visually observe scale accuracy. And another very useful aspect here is that we can use this to estimate the uncertainty of your point clouds, of your depth maps in your point clouds. We just sample a few times from the same condition latent space and calculate the mean, the standard deviation, and turns out that it actually approximates the uncertainty you would expect to get from a depth map. So things around object borders or far away are more uncertain. And you can use this uncertainty to filter out your point clouds. So just focusing on the points that are more certain and remove the ones that are less certain. On the bottom, you can see the impacts of doing this filtering approach. By keeping only the 50% lower uncertainty points, you can bring RMSE down by more than half. So if you care more about quality than quantity, this is a very useful way to sparsify your point clouds and improving quality as we're doing that. So you can target the more useless pixels and end up with a smaller, more compact point cloud that is even more accurate than the one started with. As I said before, we were state-of-the-art for a while, but somehow this whole zero-shot metric depth estimation topic exploded over the past year, as Matteo was saying. And there were lots of papers focusing on the same tasks. So we've been keeping up with them as well. And again, I won't be able to get into details because this paper is not in archive yet, sadly. But we have improved over zero depth by quite a lot. And I think we're still state of the art given the depth and things that are coming up, even though definitely is not really metric. But yeah. The idea here is to come with a diffusion model that can be properly trained on sparse data, which is something most people are running away from. Let's train on synthetic data. Let's avoid sparse real-world data. We are going another way. And how can we properly leverage all this untapped potential that are the available sparse depth maps? Won't get into details. Hopefully soon you'll be able to hear more about it. And now for my last verse, I'll talk about one of our papers that we present at CVPR, I think on Thursday, the poster. It's not exactly monocular depth estimation, but the goal here is to generate range images that follow realistic LiDAR patterns. So to achieve that, we propose a novel latent autoencoder that is designed to preserve LiDAR properties during the encoding and decoding stages in terms of patterns, geometry, and object shapes. Our main goal is unconditional LiDAR generation. So after training on specific data sets, you can generate point clouds that approximate the LiDAR patterns found in that data set. We also explore conditional LiDAR generation a little bit by providing different types of conditional information. We experimented with images, which kind of makes it similar to monodepth, I don't know, semantic maps, bounding boxes, and even texts. I have some very promising results showing that all of those indeed work. So this is an example of semantic map conditioning. And if you're curious, and want to know more, you can please stop by our poster. And thus, my ode to monodepth comes to a conclusion, at least for now. I'm sure there will be more verses. Some are coming up. Some are being written as we speak, as I was saying just now. And hopefully in a couple of years, I'll be able to come back with a new chapter or two. Sorry, there were no deep dives and in-depth discussions. I think now the goal here is to talk more about the journey, not the destination. And I think some people say that that's what matters the most. So happy to take any questions now, and I'll be around. So please reach out to me if you want to know more about any specific topics. Thank you.
quantum depth from the perspective of the speed and efficiency of trained hardware. Is that a consideration at all for?
Yes, not for any of those papers, but we are currently exploring several transfer efforts towards bringing that to actual vehicles or robots, and that becomes a huge problem. That kind of invalidates a lot of the new architectures and a lot of the latest models. But we have had some success with like TensorRT, JITs, and all the other tools that actually speed up those networks by quite a lot. Surprising amounts. So we can get real-time performance with a transformer network even. Maybe not a full-on diffusion, 1 billion parameters, but yeah, that's a huge topic in itself, how we can improve performance in this axis as well.
Imagine you could use these models as like a teacher model for a more lightweight.
Yes, so usually we have these two thrusts. One is the offline learning that produces the pseudo labels, and you have the online learning, which are the actual distill networks that we apply. But yeah, this is a good idea. You?
Got a question about the self-supervised camera calibration.
Mm-hmm.
So you mentioned that you calculate the calibration parameters on the go for each frame?
For the first paper, yes. For the new array surfaces, yes. The second one is per data set. Yeah, so we are learning one jointly across all the images from that data set. But we can switch to other data sets and learn a different model for that other data set. Cool.
Can you train with LiDAR, but when doing inference, you don't need to use LiDAR? Is that possible?
Yeah, that's when you are supervising, not self-supervising. Then you use LiDAR as ground truth, and you can train your network in that case. So yeah. And you can do both. If you do the semi-supervised routes, you have one portion of your training loss that is self-supervised, the other one is supervised, and you combine those two.
Another question, if I may. The color information, does that play a role in training at all? Would it work with monocular camera, IR camera?
We were surprised they worked that well. So usually when you are training those networks, you do some sort of color jittering. So you increase robustness to changing brightness and things like this. But I would imagine the network cares about color because that's all it learns from an image. So you're surprised that it works in such low expressivity setting. But yeah.
Thank you.
So for the zero depth model, for the metric depth, does the model learn some of the like knowledge of the general object size?
We haven't done any specific study about what it learns, but I imagine that this is the only way that it's going to be able to do this useful transfer across domains. Because now the difference from what it learns in the traditional affine invariants or supervised self-supervised model is that those only care about the image properties. So they are constrained by the camera model they're using. So if you have a wide field of view camera, the car will be larger, but the car is not larger. The image makes the car larger. So if you provide image plus geometry, you are learning 3D priors. So the car is the same regardless of how it's observed. So I imagine that it's learning some sort of object shape priors. A car is this size, and a chair is this size.
So if we want to transfer the model to some very different domain like medical images, then this won't work.
I'm imagining that it won't work. Then we need like a larger data set and more diverse to be able to go in that direction.
It's more reasonable to grab something like physical units like position.
Yes, yeah, that's always possible. That's also, yeah, that's very useful actually.
The zero depth, was it trained on a specific kind of data sets, or did you do training on?
So we train on a combination of indoor data sets and outdoor data sets. So that was already back then. Back then, so I think our main competitor at that time was ZoeDepth. That kind of has two different heads, one for indoor domains, one for outdoor domains. So it didn't need camera geometry at all. And I really don't see how that works, but they are still kind of bridging that they're still breaking those into two problems, one with a different depth range. This one doesn't really have that. We just combine everything. We need the camera intrinsics as one additional source of inputs, but it's one model for everything. And we try on tabletop settings, we tried on outdoor scenes of people walking around, and it works quite well in all of settings. But this is still a very small data set. We are currently scaling up by quite a lot, especially for the new paper.
So the aspect ratio, is it relatively like landscape or you're relatively close to each other, I guess, right?
Yes, yes.
What
So
happens if it's a portrait?
it works just the same. So when you're training, we actually resize the image by quite a lot as one additional data augmentation. So it could be landscape, could be portraits, could be any sort of, we do a lot of resizing.
Gravity with that, like the direction of gravity, like portrait means, like landscape is like, yeah, you take a landscape, but then it's not like flipping the image. But
That's true. I don't know how it works if you provide an image rotated by 90 degrees. But if you provide an image that is on the right axis, but it's portraits instead of landscape, it should work just fine.
Right. How about we break, because there's a 15-minute break,
yes.
but Victor's around, yeah, we can have follow-up questions.
Yeah,
We'll be
please.
around for the next 10, 15 minutes.
Yes.
So, thank you so much, Victor.
Thank you.
Hello. I have this question. Thank you very much for the presentation.
Hey, Ripu, can you hear me?
I think they might have headed out for the break. So I think
Yeah.
we
I was
should be
going to
back
tell
in.
maybe we can have the break until 3:40 because we are a little late, so we can have the break a little longer.
Right. Yeah, I guess if we can get in touch with them, we can check. I guess it depends on what's going on in person because I think we're lined up so that there's the CVPR break as well.
Yeah.
So yeah, we'll see.
I'm just going to pop away for a few minutes while the break's happening.
Matthew, can you hear me?
Yes, can you hear me?
Yeah, are you ready?
Yeah.
We'll start in 1 minute.
Okay, I will share the screen meanwhile. Okay, let me know when to start.
All right, so we're going to start with the second half of our workshop. So Matthew Foggy, he's going to share more about our monocular depth estimation challenge, and then we'll have the challenge winners come and present in the workshop. So Matthew, you want to get started?
Okay, thank you, Ripo, for the introduction. So in the next 15 to 20 minutes, we will talk about this third edition of the Monocular Depth Estimation Challenge. And we will start by briefly recalling why it is important to have a good benchmark for monocular depth estimation and in general for any task in computer vision. We will take a look at the main components that are important for having a reliable and a solid benchmark. Then we will introduce the actual monocular depth estimation challenge benchmark, and we will look at the results for this year edition with a very quick overview of all of the participants and the main trends that have been followed by any of the teams. And finally, we will conclude with some take-home messages that we can take from this year edition. So before we start, it is worth mentioning that in the past years, in particular for the self-supervised literature that we discussed before, both me and Vitor, let's say we had some issues with the initial way we had for benchmarking the results. Indeed, most of the evaluation were limited to a single dataset, which was the Kitty dataset. And the evaluation protocol itself was affected by several failure points. And among them, we will appreciate in the next minutes how the ground truth that was used most of the time was actually often not entirely correct. And we will also see how many of the metrics that are common in the papers and are still used very often nowadays are sometimes uninformative or saturated by the Kitty benchmark itself, as well as we will highlight also some not correct practices like running ablation studies or hyperparameters tuning on the test set, as well as comparing with very different methodologies when actually the methodologies themselves are not fairly comparable. So we will start by having a look at the ground truth, and of course, this is why we started from the ground truth, because actually the ground truth is the core of a benchmark, and if we don't have an accurate ground truth, as a consequence, the entire evaluation we will carry out will be, of course, not correct. And at the very beginning of the self-supervised literature, the raw Kitty dataset was used as proposed by the Huygens paper as the standard benchmark for evaluating single image depth estimation. And the so-called ground truth depth for this dataset was obtained by means of the raw LiDAR scans made available by the dataset itself. However, these scans, despite being quite accurate to some extent, they expose some critical weaknesses, and we can resume them into two main pain points. The first one is that the viewpoint at which the LiDAR collects the depth labels is not perfectly aligned with the image viewpoint. This means that the LiDAR scans are projected over the camera plane, and this produces some occlusions that we will look a little more in detail in a while. Furthermore, the LiDAR scans, as you can appreciate here, are quite sparse. So our ground truth is indeed sparse, and this will produce some very inaccurate boundaries at the objects. So these very first issues often make the evaluation on the Kitty benchmark to some extent quite biased. Now I'm going to zoom a little more into this. This is a detail from the previous LiDAR map, and probably you can figure out this is a car parked on the side of a road. And these small points here, being both yellow and blue, are basically LiDAR measurement from the background and the foreground that are mixed up together. And this happens when you reproject the LiDAR points over the camera plane. And this effect is actually caused by the occlusion of the car over the background. Indeed, since these LiDAR scans are indeed sparse, the final result will be having them merged together in between the foreground and the background. Of course, your monocular depth network, by seeing a car, will predict some kind of consistent depth for the car. But when you evaluate it, you will have also these outliers coming from the background that will give you a higher error, even despite if your prediction is actually correct. This is another example for the left side of the road. And as you can also see, in addition to the occlusion, we don't have clear boundaries between the car and the background. So our accuracy, the accuracy of our prediction and how good our model is at dividing the foreground from the background cannot actually be properly assessed on this kind of sparse labels. And for these reasons, a good benchmark should take into account better ground truth annotations. And for this purpose, James and his team, for the previous edition of the Monocular Depth Estimation Challenge, used the Sudaptom York Natural Scene dataset, also known as SYNS, which consists of several LiDAR scans being collected into panoramas and being collected in a very dense manner. Indeed, here we can notice how for a single panoramic image, we can obtain very dense ground truth depth labels. And these labels are obtained mostly in outdoor environments and are very, very dense. However, there are a few pain points even for this kind of benchmark. Indeed, to collect that dense annotations, we need to scan the scenes multiple times. And this means that actually, if we have some moving object appearing while we are scanning, of course, we will have some inconsistent depth being accumulated over time. Nonetheless, Jaime and his team sampled some portions of this dataset and generated the so-called SYNS-Patches dataset. And they simply took the panoramic images and they sampled every 20 degrees at the high level to obtain some patches like this. So here we have an example from a forest, and we can appreciate how the annotation for the trees are very, very accurate, and they are far beyond what we could get from the Kitty dataset. On the right, we also have an example for a scene in which we had a moving object. Indeed, we can see the color image on the top, and at the bottom we can see some kind of silhouette that actually not correspond to a car. So this is what I meant before for moving object coming into the scene while the scanning is taking place. And for this kind of scenes, of course, manual filtering was of course necessary for removing the errors in the annotations. And this is a zoom into the detail I just said before. And from this dataset, together with extracting color images and dense ground truth depth maps, it was also possible to obtain some edge boundaries for the objects in the scene. And this is particularly important for assessing the accuracy of the monocular depth estimator, in particular at the depth discontinuities. So, so far we have talked about the ground truth, which is of course the very basic of any benchmark, but also the metrics are very, very important. Indeed, for having an accurate evaluation of any of the methods that we are going to benchmark on our dataset, we need to also have meaningful metrics. And for what concerns the Kitty dataset and the standard protocol used by many papers through the years, of course, we had some issues also with the metrics. Indeed, some of them were not entirely meaningful. Some of them were also not entirely correct. For instance, for the squared relative difference, we were missing some kind of square term at the denominator. And more importantly, some of these metrics, despite being informative at the very beginning of the research on this field, nowadays are quite saturated. So they are no longer meaningful of the differences between the state-of-the-art approach in coming out year by year. So for this purpose, Jaime and his team, when proposing the benchmark for the molecular depth estimation challenge, they favored only those metrics that are more meaningful and, more importantly, also more interpretable. Like, for instance, the mean average error, the root mean square error, and so on and so forth. Furthermore, another legacy from the Kitty benchmark is that most of the evaluation were conducted directly on the depth map. That means that basically the error was computed with respect to the single pixel depth rather than computing some errors on the overall 3D reconstruction. And since estimating the depth is instrumental for actually 3D applications, probably estimating some more meaningful metrics on the 3D space might be a better choice. And indeed, Ornek et al., almost concurrently with the first edition of the Monocular Depth Estimation Challenge, tried to revise the standard protocol and proposed to use some point cloud-based reconstruction metrics. In particular, they were using the F-score and the interception over union based on the precision and recall computed with a 10 centimeter accuracy threshold. And following this strategy, Jaime and his team also decided to evaluate the accuracy of the estimated depth at the object boundaries by using the depth boundaries extracted from the dense ground truth labels. And in particular, following the IBM's benchmark, they proposed to use the chamfer distance between the predicted and the ground truth boundaries. This way, they could have a good measure of how precise was the division between, for instance, the foreground objects and the background. So after talking about both the ground truth and the metrics, now let's introduce the monocular depth estimation challenge, which is built over these two main components. So this challenge takes place over the SYNS-Patches dataset by selecting only a subset of the most informative metrics. And together with the challenge, James and his team also implemented an entire framework allowing for a fair comparison between all of the existing approaches from the literature, as well as any new coming state-of-the-art approach. And one key property of this benchmark is that the evaluation is completely centralized. Indeed, the benchmark provides a validation and a test split, and for both of them, the ground truth is completely hidden to the developers. This way, the developers are forced to submit to the online benchmark, and they have no access at all to this kind of information. So it is not possible to cheat, it is not possible to fine-tune the model or to tune the hyperparameters of your method. And these are some examples from the SYNS-Patches dataset. Here we can appreciate the very fine details in the ground truth maps, as well as the depth boundaries extracted from the ground truth depth themselves. And we can also notice the mixture of different environments that characterize this kind of benchmark, being both a mixture of indoor and outdoor environments. And with the development kit, James was also very active at improving the existing baselines. And in particular, he implemented up to 16 state-of-the-art algorithms in 2022. And he also revised most of these frameworks with some improved design strategies that, of course, came out through the years. And just to give an example, the very baseline of this framework is the very first self-supervised paper I introduced a couple of hours ago. That is the one proposed by Garg et al. And James basically just revised the common backbone used by Garg and slightly improved the supervision tricks used to train the model. So this baseline represents the very bottom point from which we start the evaluation of this challenge. So now let's give a look at the results and also draw some conclusions about the outcome of this third edition of the Monocular Depth Estimation Challenge. This year we got an explosion of the participation to our challenge, and in particular we had up to 20 teams participating into the final development, into the final testing stage. Among these 20 teams, only 10 of them actually submitted a description for their method, and they are reported in this slide. And among these 10 methods, we will figure out in a few minutes that most of them share one very same approach that we have already introduced several times today. And indeed, here I'm listing the 10 methods, and I'm highlighting in blue one common point that has been exploited by most of the approaches. Indeed, 6 out of 10 basically started from the depth anything model provided by the original authors, and they extended the depth anything model with some different techniques. In particular, the winning team used some stereo proxy labels, so they obtained some disparity maps from stereo images, in particular on cityscapes, to fine-tune the depth anything model. And any of the other had just some small variation on this team. So the second team used an auxiliary network and used the self-supervision on the Kitty dataset, while the third one used some metric module for estimating metric depth, and they ran a fully supervised fine-tuning on NYU and Kitty dataset, and so on and so forth. We would also like, nonetheless, to highlight that 4 of the participants also proposed new techniques. In particular, we have the 5th team that deployed a custom model that has been published in parallel to the main conference the CVPR. So probably you will find out this paper in the next days through the main conference. But we also had some other additional approaches using some Swin transformer for learning how to estimate depth. And finally, we have a very peculiar approach based on a segmentation model and some statistical models that, starting from the segmentation masks and some priors, learns to extrapolate some depth information by using the cityscapes dataset as the training dataset. Among these participants, we selected 4 invited speakers that will take their talk just after this presentation. And to favor the diversity among the participants, basically we selected, of course, the winning team, as well as we selected the EVPP ++ method, which achieved very good results. Then we favoring diversity, we invited the team using the eco-depth model. And finally, we also invited the Elder Lab team, which used this very particular approach, which is completely different from any of the above approaches. And before leaving the word to our invited speakers, I'm just reporting here the results by the challenge. So Pico MR is the absolute winner of the challenge, since the main metric over which the winner is selected is actually the one on which they achieve the best results. And then they are followed by 3 more teams using the pre-trained depth anything model. And this is already suggesting that using this kind of foundational model represents a very strong prior for facing this challenge. And then so on and so forth, we go through the bottom. And in particular, we had the EVPP++ method that was very, very strong on the depth-based metrics at the expenses of the point cloud-based ones. So we decided also to have them as the invited speakers because of their very exceptional results on the depth maps accuracy. And to draw some conclusions, we can notice how the F score achieved by the absolute winner is has improved by 62% over the original baseline, and already by a 35% with respect to the previous winner of the 2nd edition. For what concerns the absolute relative error on the accuracy of the depth maps, we can observe nearly a 60% improvement by EVPP++ over the baseline, and still more than 27% improvement with respect to, of course, the winner of the 2nd edition. So we can appreciate how the introduction of this foundational model, such as depth anything, allowed for boosting the accuracy on this benchmark by a very large margin. And here we are showing some qualitative results about any of the methods participating into the challenge. We will focus on the top 3. And despite the use of the strong priors by depth anything, we can still figure out that we are still missing something. Of course, in the forest, we are recovering a little better the details with respect to self-supervised approaches or the supervised approaches from the 2nd edition, but we can still figure out some artifacts. In particular, also both the first and the 2nd method are showing some grid artifacts that probably came out from the fine-tuning they conducted over the depth anything model. And of course, we can still figure out that most of the edges at the object boundaries are still far from being very sharp as they are supposed to be. Here are some additional examples. And again, we can notice how, okay, we can figure out a little better details. But yeah, I think there's still a lot of room for further improving the results. And this concludes this talk. Before, again, leaving the word to our invited speakers from among the challenging teams, I would like to draw some personal conclusion. So yeah, in this year edition, we witnessed a completely conquering of the stage by the foundation models, in particular by depth anything. And we feel that the web scale dataset used for training depth anything played a crucial role into making it the standard choice by 6 out of the 10 participants. And we also observed that despite 6 of them used the depth anything, we also came out with very different fine-tuning strategies. So I would say none of the 6 teams used the very same fine-tuning strategy, but we can say that this fine-tuning strategy plays a secondary role, yet it makes some little difference in the final leaderboard. And to conclude, we can figure out as well from the, as we have seen from the qualitative results, that the thin details and the depth boundaries remains challenging, even if we are using some foundational models. So that's all for this presentation. Feel free to ask any question. And of course, thanks for your attention.
Right. Are there any questions regarding the challenge? Okay, I think we can move on to our presenters.
Okay, perfect. So according to our schedule, the first 2 presenters should be connected online. The first one is Mikola Lavreniuk. Sorry for my pronunciation. Okay. Thank you very much. Feel free to start whenever you're ready.
Okay. Do you hear me well and see my screen?
Yeah, loud and clear. And yeah, we see both the screen and the pointer.
Okay, good. Hello, everyone. My name is Mikola Lavreniuk, and today I would like to share with you my competition journey from the start point and to the results that I get. So the baseline model that I choose, it was ZOE-DEPS model, because I have the experience working with it, and it is very easy to use and provides good results. So it consists of encoders that is pre-trained on a lot of data sets, and the specific decoder that solves the problem of metric depth estimation, not like a regression, but more like a classification using the metric beans approach. So using this baseline model, I overpass the baseline that was provided by the organizers, and from that point start exploring the alternative models to improve accuracy more. So what I start checking, it is the best models on the Kitty dataset. So I selected the self-supervised model for Monocular Depth Estimation called SQL Depths, and it was like on the moment I have checked, it was like state of the art on the Kitty dataset, and the main idea is, as was mentioned on previous presentation, so it consists of a depth network and post network that jointly train together on the unlabeled dataset, and after that, when this model trained, the authors fine-tune in it on the depth maps from the Kitty, and I tried this model for the competition, but for my frustration, I found that it has lower result comparing to ZOE-DEPS. And even when I tune this model and get better results on Kitty's than original authors had, it is still lower than ZOE-DEPT. So moving forward, the other models that I looked at it was VPD models. That is, from my knowledge, it is the first model who utilized stable diffusion model to solve the depth estimation and other tasks like semantic segmentation and so on. But the main problem with this model is that it is utilizing the text encoder, and the author of this model, they used text templates, and for this you need to have a class name. So it could apply for NYU dataset, but it could not apply for Kitty or SYNS dataset. That is why it is like our custom model called EVP. So what we did, we solve and tackle this problem with these classes with two different approaches. One is to utilize some model, for example, like Blip version 2, to generate the text description from the model, and after that just use this text description to put it to text encoder and make this pipeline working. Also introduce additional model based on the multi-attention refinement of the features to boost the accuracy. And alternative approach is to use directly without text encoder and without any text, just directly use clip encoder to get embeddings from the input image, and these embeddings, thanks to clip, are very close to embeddings of the text, and using this it could produce the results for the depth maps, very good results, and without need to have some classes or some text on the dataset. That is why it called like EVP++. So with this model, I have get like much better result, and still looking for new models. So after that, I found like depth anything. So I will not be stopping here for a long time. It is the same code base as ZOE-DEPT, and they change only the encoder from bait to WIT encoder that trained on Dino V2 and utilized a lot of data for training. This model provides me like a better result comparing to EVP++, but the difference was not very big. But in general it is better, so I decided to stop on this model. And after that, I was trying to do local detail enhancement and try to investigate some approaches for this. So I started working on boosting depth. It is a model for enhancement of the details like edges. You use depth model for whole image, and after that use your depth model using sliding window technique, and after that using the GAN model, you merge the results together. But this model did not provide me better results. So the results are pretty looking, but not improving the metrics. After that, I tried like state-of-the-art patch fusion models that is new one, and it do in the similar way, but like different models for coarse and fine results, and after that like fusion model for combining them. It provides much better results comparing to the previous one, boosting depth, but the result was still lower than EVP++ without it and depth anything without it. So my final solution that I get the best result was use depth anything with width encoder and the depth metric beans and fine-tune it on indoor and outdoor dataset. So it is provided the list of them with standard loss and augmentation. The best training options that I could found is provided. And the other tricks that I used just sliding window. So without any fusion model, neural network, I found that it is improving the result from depth anything much better than comparing to any like previously mentioned methodology. Also, I turn off the TTA that is by default turning on in depth anything, because with TTA it and the same for the model soup. When I aggregate like several different models, I get much better, not much, but somehow better accuracies for like RMSE or like other, but not for F1 score. So I decided to turn it off and also turn off the padding of the input image. So what did not work for me is, as I mentioned, like some models that are much higher accuracy, that has much higher accuracies on KT comparing to any depths or to EVP, but they are failed here. I think it is main reason is due to transfer of domain, and this two models like EVP and depth anything, they have pre-trained on very large amount of data, and that is the main reason. Also, larger image resolution and longer training did not help me. Also, some advanced augmentation like random crop or cut flip from specific depth paper did not work. As I mentioned, some dedicated models for edge or local details enhancement failed, and I finally used only like sliding window without any other post-processing. TTA and model soup also improve like other metrics, but not F1 score. So I just rearrange on the table and to add the column like total rank to summarize all the places. So if you get like here 4 + 3 + 1 1 + 3 + 5, I get like this column, and shows that this approach is not like perfect in terms of F-score, but in general, if we are like combining the methodology using all like metrics, it is on the first place, and also it is the only one who has like more than one top one places, and also all the metrics are at least 5th place and higher. Yeah, according to qualitative results, when I comparing like depth anything and my results and, for example, patch fusion. So for like visually, the best results was for me this patch fusion. You could hear like very good details comparing to these two models. And for example, here this model found the details like grid cell on the windows, but both models like failed and it is not found. But when you are looking on some other parts, like here's a pole, but this model did not found it, and here you could see like more clear the structures trees, and so it is not in every case it is obviously better, but in general for like a lot of images it is better. But when I comparing the metrics, it is a lot lower comparing to like any depth or EVP++ model. Yeah, so thank you very much. And if you are interested, I publish the code for final solution. You could find it like here.
Right, we may have time for one question if anyone has. Okay, and I think we can move to the second presenter.
Okay, the second presenter should be online as well. Should be Guangyan Zhu. Sorry for my pronunciation. Perfect. We see your screen.
Can you hear me?
Yes, perfect. But we see the presenter mode.
Okay, how to change this?
Perfect.
Okay. Hello, everyone. I will introduce our work. High quality data makes great progress. I'm from Pico MR. First of all, we are looking at existing works. In general, there are two main directions: relative depth and the metric depth estimation. Relative depth estimation, it needs diverse depth data set. Then it will use scale shift invariant loss in pre-training. There are many works use same pipeline. The first one is Midas and Laris. Then the ZOE depth and the depth anything. The latest is Marigold. It uses a diffusion based model, but this kind of method have some problems. They are limited in useful. They have limited useful in reality because it has no physical distance. Then it's a metric depth estimation. The training and the test on the same data set, like the first figure, it has a poor generalization, but it performs high quality on 3D matrix structure. To solve the problems, the matrix 3D consider the camera parameters into the network training. Also, the zero depth, it input the camera parameters to send to the network. But this kind of method just consider the camera difference. It ignores the sense difference. It means if we use the same camera, we just take the picture of indoor. It's difficult to transfer to the outdoor sense. So the matrix 3D extend its work. Matrix 3D V2 use more data set. Then we will look at our method. Just like I said before, there are two difficulties. The first one is the different sense. The second one is the different cameras. How to solve these two problems is also the key to all the model depth estimation. For the test benchmark SYNS-Patch, it includes indoor sense and outdoor sense. Outdoor sense include natural, urban, and agricultural, etc. sense. It's very difficult to solve the different sense together. The second one is the camera difference. In the open data set, the camera parameters is different and is also different from the test data set SYNS-Patches. So how to transfer the open data set to the test data set is also a key problem. Our framework is based on ZOE depth, but we change the backbone from Midas to depth anything. It's just a little change. the same, the rest is the same, like depth anything. The backbone we use the BEIT 384 large backbone, and the head we use zero depth based metric depth metric head. And then we use proximity labels. The resolution we keep bigger. Also, we just keep 1024 and 2048, which is different from input image size. Indeed, we also do the experiment keep the same 3084 plus the 7068, but the result is worse than the big resolution supervision. Indeed, we select the data set. We have 3 steps. The first step is quality evaluation. The second step is diverse data set selection. The last one is necessary data selection. For the first one, the quality evaluation, we should consider 3 factors. The first one is the accuracy. The second one is coverage. The last one is density. The accuracy, it means the labels should access method. I will introduce in the after. Okay. Under the mean shift, we will use the data selection because it has many data set. How to speak it? Many data set has the same sense, so we need to filter the unuseful data set. The last one is just used to select necessary data set. It's an inset from large language model. We just apply it to the image process. The second one is the gradient angle loss. We design a new modular loss. It is very useful for planar supervision because it has a big supervision around 0. Traditionally, we use gradient loss, but it just supervises the gradient of x-axis and y-axis, but the angle loss it ignore the scale. The gradient of y-axis and the gradient of x-axis, they will divide, which will eliminate the scale. It's so it's useful. Then we will look at the result. To select a best model, we evaluate the result on 5 benchmarks: KT, VKT2, cityscapes, diode, and NYUV2. We use 6 data sets to select the best data set, perhaps. Then we find the cityscapes has the mean best alpha 1 and F score than the cities. Also, it has more information because cityscapes has more density. Its access method is SGM, and its coverage is larger than other data set because cityscapes have 50 cities and in different countries. The other data set just use less cities and in one country. Also, the numbers have much, so we choose cityscapes. Then we also do the experiment of mixed data set. We found that only use cityscapes have a better result than cityscapes with Tata Air and cityscapes with KT. So we just choose cityscapes as the baseline of our method. Also, we do the experiment of different backbone. we use zero depth based backbone is unstable to training, and use depth anything based backbone. It enhance overall performance, especially the F-score. Also, we do the experiment of loss function. We use 4 loss function: C-log, SSL as RPNL, and greater angle loss. The C-log plus SSL is also demonstrated by metric 3D V2. We also have the same conclusion. It is useful, and RPNL as used before. We will see use 4 loss. It has a strong enhancement in F-score. So we concentrate more the F-score, but the delta one is worse. In the end, our result get the first place, and the hyperparameter of greater angle loss we set 5 have a better result. Okay, thank you. Any questions?
All right, in the interest of time, we'll just skip to our next presenter.
Okay.
We're running a little over, so if you can keep it up to 10 minutes. It's good.
Do you have an laptops
For
this user?
yeah.
I can
We have videos, right?
do I need to connect it? I can just share it, right?
On Zoom?
Yeah.
Sure. You can unmute yourself. So
It's not visible. Yep. Okay. So hi everyone. Thanks for being here. I'm going to present our method called EcoDepth, which got us the 7th rank on the 3rd Monocular Depth Estimation Challenge. So we represent the Vision Lab at IIT Delhi, hence the name Vision IITD. This is the team comprising of myself, my co-author Suraj Patni, and Professor Chetan. Right. So this is a quick demonstration of our method. So you can see the RGB image on the right hand side of the on the right side, and the corresponding depth map on the left side. So one striking difference between this our method and the other methods that there's some I see. Yeah, it's not that smooth. So one striking difference between our method and the other methods that most of all which seem to use depth anything is that our method captures very fine-grained information which is absent in other methods, as was highlighted by Matteo in his talk. Right. And so our method was published in CVPR 24 main track, and you are welcome to come to our poster session 6 in ARC 4AE, right? So yeah, so quite a lot of methods that we saw today use diffusion, use a unit as the information extractor, and we also follow so some examples of such methods are TADP and VPD. And the reason why diffusion models seem to be so popular with dense prediction tasks is that they have been pre-trained on a large number of image text pairs, which which instill in them a strong prior for visual tasks, in particular depth prediction tasks such as depth estimation. So these are the TADP and VPD papers which inspired our work. You can check them out. The links are below. So the question which comes up is, what is the best way to condition the unit in the absence of ground truth text? So so the in diffusion, in stable diffusion, you start with text and an optional initial image, and then you produce the final image. But in our case, we only have the initial image and we don't have the ground truth text. So we carried out an ablation on the different types of embeddings that we can pass into the unit. So one method was to pass the scene label embeddings. The second one was pass text captions. So this is similar to what I think the EVP EVP participants were doing, that they initially, although not in their final method, so they were passing the text from the blip to passing the image into the blip to captioning system, and then passing the generated text into the unit. But I noticed that they later also mentioned that they directly wanted to compute the embeddings and pass it into the unit. So our method is also similar, but we don't use clip. We directly pass the image into the VIT and use a series of MLPs to align the embeddings to the clip space to generate the proposed scene embeddings. So one question that you may have is, why do you want to align it to the clip space? Well, that's because in the pre-training paradigm, the text is passed into the clip model, and then the embedding is passed into the unit. So there's a strong prior for having the embedding in the clip space. Yeah, so that's why aligning it is important. And some things to notice over here is that there is no clip. So in TADP, you can see TADP on the left, you can see there's a clip step, and in the in VPD also, although it doesn't seem to be shown over here, but they have clip inside it. But we directly pass the VIT embeddings into the unit. Yeah, and alignment to clip space happens through MLPs, as I already mentioned. There is no intermediate text, so there's no loss of information, which happens due to passing the image through a captioning system which generates text, which are discrete labels, and everything happens in the latent space. So there is no as such loss of information. Right, and as I showed in the video before, our model seems to capture very fine-grained information. So this might be due to the no intermediate texts being used. So this is the overall model architecture. We use the side module, which I just showed over here. This is called the side module. We pass you pass the image through the side module and to generate the context, the condition, and the rest of the pipeline is just is motivated from VPD. I've attached the source. So these are some of the qualitative results. This is the NYU depth V2 dataset. This is an indoor dataset. This is the Kitty outdoor dataset. And these are the zero-shot generalization results. So Sun RGBD, IBIMS one, diode, hypersim. So some questions in our GitHub repository came up about comparison with depth anything. So it seems that on on tasks like NYU and Kitty, our model seems to work at par with depth anything, but on zero-shot generalization, depth anything works better, possibly because of large-scale pre-training. Yeah. So in our case, we don't do pre-training. We just use the stable diffusions pre-trained information and fine-tune on the NYU and Kitty datasets separately. Right. And these are the results on the NYU depth video dataset, Kitty, zero-shot generalization. I'm skipping over these in the interest of time. So this is the MDEC challenge. So as I mentioned earlier, you can see the fine details captured in the, the first column is the RGB image, the second is the ground truth depth, the third is the predicted depth from our method. And you can see the, like, the how intricate the predicted depth is, which does not seem to be the case for depth anything based models. So this is the standing, our standing. We stand at the 7th place, but as you may see that there is no dagger against our entries where a dagger stands for pre-training using depth anything. So I think that makes our model special, unique. So right, and thank you. So any questions?
We have one more presenter. We have one.
Is the last presenter there, Ripu? Because actually for the information I got, the fourth presenter should be there in person, but I see also one of the participants being online, which is Hossein, right?
I think you're muted, or at least we can't hear anyone
Yeah.
talking.
Yeah, we can't hear you. If you are talking in Seattle, we can't hear you.
I think somehow they can't hear us either. I've messaged
Can you hear us
Resource.
now?
Hello?
Can you hear me now, Simon?
Yeah, there was a bit of echo for a moment, but can you try again?
Yeah.
Whose microphones are on? Because if both of you have it on, it might be echoing. No, we're back to not being able to hear.
Yeah, me neither. Yeah.
We're just figuring out the echo. So
Can I turn mine back down? That's what I was trying to do. Audio settings are. Can you hear me, Simon? No. They can't hear me.
We can hear you, but again, there's still a lot of echo.
So is the echo from your?
yeah, there's a
Maybe you can speak from your microphone.
we have unmute. Okay, so we'll try this. Can you? Yeah, you can go ahead. I'll just take the laptop here. It should not echo.
I think that's even better.
Is this sounding okay?
Yeah, that's better. Thank you.
Thank you. Sorry about that. I'm sorry. Okay. Sorry for the delays. Okay, so this is really the work of my graduate student, Sani, who couldn't be here, unfortunately. And as Matteo mentioned, it's a very different approach. Our goal is now really to
click on the other screen.
goal is not really to compete on the benchmark, but rather to explore some ideas that maybe will provoke some new kinds of research in monodepth. So let me first give us a bit of background. So the instigation of this project was partially this paper that we worked on a couple years ago. The student, Southampton University, Anderson, a great student. And conventionally in human perception, it's been thought that spatial understanding kind of precedes and informs semantic understanding. So we compute kind of spatial gist of a scene, and that gives us sort of a 3D spatial layout, and then semantics follow. And in this work, this like physical work, we found some interesting results suggesting that actually, to a great degree, it's the opposite, that semantics were informing our perception of 3D space. So that's one of the key ideas, is to what degree semantics inform monodepth. And the other main idea is an old idea that I'm sure everyone's aware of, which is that the ground surface is extremely important in determining monodepth perception.
So if we have an observer with a horizontal optic axis, then there's a plausible relationship between depth on the ground plane and ground terrain and height of the image, right? Things that are behind the image tend to be further away. And that's a very strong cue. This is shown by the plot on the right here. So this turns out to be used really profoundly by humans. This is shown in the plot on the left here. We're plotting the correlation of human judgments in blue with the higher is further Q. And we're also plotting a bunch of mono-depth networks. These are somewhat old now, showing that they also use this Q to varying degrees. This is not a new idea. This went back to the 20th century, Jeff Jacobson's ground theory. So we're going to call this this talk ground theory talk. And the question is an academic question of to what degree can monodepth be reduced to semantics and ground theory? Now, obviously, it cannot be entirely reduced to these things, but we think it's useful to try to extract as much out of these two things as we can in an effort to understand how monodepth works. So to do that, we've produced a simple pipeline that makes some pretty strong assumptions. First, we'll assume that the camera parameters are known or can be accurately estimated. There's very good methods for doing that. We'll make the gross approximation that object surfaces are known as vertical. And we'll make an assumption that if you see an object that's in contact with the ground image, that it's resting on the ground in the scene. These are all things that are new in moving perception. Okay, so I'll quickly walk through the method. So we're going to use an off-the-shelf semantic segmentation system. In our case, we chose an image. We're going to aggregate a set of classes into a supercategory of ground classes. Okay? So then we'll use that supercategory to segment the ground surface from the rest of the scene. And this is the end of deep learning in our framework. So we're really interested in, from that semantic segmentation, how much can we get in sort of using sort of retro computer vision methods with very low machine learning. Okay, so the other thing we do is with the semantic segmentation is use it to partition between indoor and outdoor scenes. This turns out to be fairly easy with a maximum likelihood multinomial classifier based upon the semantic classes. That works very well. So now we can consider indoor and outdoor scenes separately. So the first goal is to estimate the depth of the pixels underground. So we can do this using just simple projective geometry. We find it's a bit better to use a learned kernel regression profile, depth profile, which just reads off depth from height of the image. So that fills in the depth on the ground surface. Okay, so then the next assumption was the contact assumption. So that semantic segments that are in touch with the ground segment will inherit the ground depth. So it's assumed that they're resting on floating. So that extends the number of pixels at which we have depth estimates. Okay, there is a problem with objects that are very close to the camera, so the ground's not visible below them. So for these, we currently learn class conditional expectations of the steps. Okay, now actually, one quite important feature that we use in this method are line segments. So we are using a state-of-the-art method for detecting Manhattan and non-Manhattan segments. There's sort of two cases. So the method we're using is called FR. Is a pretty good estimate of the reliability of the Manhattan frame. Of course, in the SYNS data set, there are urban scenes, but there are also scenes of forests and lakes and so forth, where the Manhattan frame is really not reliable. So if the Manhattan frame is deemed reliable, then the algorithm is for the Manhattan segments. if they overlap pixels on which we already have depth estimates, we can use those estimates to scale those lines. We already know the 3D orientation in the Manhattan frame, but we can use it to scale the lines. For the non-Manhattan lines, we can use those depth estimates to both scale and rotate the lines in 3D. If the Manhattan frame is unreliable, then we'll just use the existing depth estimates to both scale and orient those lines in 3D. And you can see at the bottom here that further extends the pixels at which we have depth estimates. Okay, so that's pretty much it. And then it's a matter of completion. So we use a simple class completion. So all the pixels at which we have depth estimates act as forcing terms. These are the key sources. The semantic segmentation is important here that we use the boundaries of the semantic segments as reflection conditions as well as the frame of the image. That's quite important as well. Okay, so that produces a completion on the state law. Okay, so that's the method. Pretty straightforward. It's all vintage computer vision aside from the semantic segmentation. So how well does it do? Okay, so here's some qualitative results. We're just comparing the Zoe depth here. You can see that what we call the ground theory method is on top. It produces something reasonable. Definitely you can see less detail, of course, because of the simplifying assumptions. But of course, when we always have to be careful when we look at detailed depth maps. You don't know if the detail is correct, right? Our brain is kind of interpreting it as better, but it's not necessarily metrically better. Okay, here's two more examples, which give you a sense of drawing the left and the right. Okay, what about quantitatively? So first, let's look at the ground surface. So we've broken it down into outdoor and indoor here. And as I mentioned, we tested two methods for estimating the depth of ground pixels, just a projective geometry method and a learned kernel regression model. The kernel regression model works better. We can talk about when it is. We do better than Zoe depth on the ground terrain, but we're not competitive with metric 3D on ground terrain. That's fine. For indoors, there's a similar story. We are much better than Zoe depth, but not competitive with metric 3D. Okay, so then what about the whole scene? So here we use scheme a bit. We're not competitive with Zoe depth for the whole scene, so because of the gross approximations we're making with the surfaces that aren't on the ground. But still, I don't know, it depends on if you're glass half full person or that kind of thing. This is sort of the problem that is part of with basically no machine learning. So one thing I did want to stress here is what we found that was interesting was the lines were very helpful. So if we don't use these line segments, our MAE comes from 37.6% to 52.1%. It's pretty shocking degradation. So it suggests that line segments, Manhattan and non-Manhattan, are quite useful. Okay, so that's it. So summarize, we were surprised that we could get fairly reasonable metric depth maps without learning. The key ingredients were good semantic segmentation, ground surface estimation, line segments, and this semantic boundary aware completion. And we hope that this will just generate some votes and thought and for us to be useful for better explainability, generalization, and perhaps building larger models. This could be, for example, starting point for residual computation of more complete depth. Okay, thank you.
Right. Apologies, we're running about 20 minutes late. So our next speaker and our last keynote speaker for the day is Eric. Eric is a staff scientist at Niantic, the Pokemon company, working on the light shift visual positioning system. He works at the intersection of machine learning and computer vision, 3D vision in particular. His research involves topics around visual relocalization, pose estimation, end-to-end learning, robust optimization, and feature matching. He publishes his research in top conferences in vision, where he's also an active reviewer with several outstanding reviewer mentions. He has co-organized several tutorials and workshops on visual relocalization and object pose estimation. So welcome, Eric.
Thank you so much for the introduction.
You're
Up, I think I probably
might need this.
Is
Do
Zoom
you have
already?
audio?
Sorry,
Do you have audio? No, right?
is it not recording from this or?
I'm saying, do you?
Yes, we can
audio
hear you.
for
We can.
presentation?
No. So sorry, is Zoom hearing me or not?
They should be. Can you have you unmuted yourself?
I think so. But can someone check in Zoom whether someone says that they can hear me?
So we can hear you, but I think it was through Ripu's mic.
And is this thing?
Can you hear us
Yeah, I can hear you.
on Zoom?
Can you say something again?
I think so. It should be.
Let's assume they can hear
Yeah,
me. Can you hear me as well?
Yeah, loud and clear. Yeah.
The mic. Yep.
Now, is this no?
Yeah, that's
now.
perfect. Yeah.
Now it is on. Okay. So thanks for the introduction. My talk is called Metric Depth for Instant AR. Yeah, that's too far. No, of course. Yeah, let's do it like this.
Presentation on the other screen.
Okay. Yeah, no, this thing's also working. Okay, now we're set up. Sorry. I'm Eric. I'm a staff scientist at Niantic. You might know Niantic from the games like Pokemon, Monster Hunter, Pikmin, and so on, but it's an AR tech company. And also the games, they combine elements, or they include AR and try to combine elements of the real world and the virtual world. And games are a good opportunity to do this today, but we are generally interested of pushing forward what's possible with to do with AR today. And as such, Niantic has a sizable research team, and parts of these researchers, they work on depth estimation. So some of these works, maybe you know, monodepth, ICSV19, single view depth estimation, which was later extended to multi-view depth estimation, many depth, and CVPR 21, and then going to full 3D reconstruction with simple recon here, ECSV 22. And maybe you can understand the relation to AR, because if you want to place virtual content in a scene, you have to understand the 3D geometry of the scene to place it in plausible locations. So, for example, what you can do is, if I want to place a virtual object, I first need to understand where I can place it, where's the free space. And then I can use depth estimation to render plausible occlusions, which is important for immersion. So my talk was called Instant AR. Is this instant? Yes. I can do this immediately. I can drop in my phone. I can place something. I can render realistic occlusions. Perfect. Thank you very much. Talk is done. No. If you watched closely to the paper titles which were on the slides, I was not involved in any of these brilliant works, unfortunately, because I work on something else. So when I talk about instant AR, what I actually mean is instant shared AR. What does that mean? Well, imagine you go out with a friend. You take a walk, and then maybe you go to a beautiful place like this. And then your friend says, oh, I want to show you something, but I want to show it to you in AR. So your friend places some content in his view or their view. And now we want to show this content in your view. So what do we need to do? Well, we need to project this virtual content into your view, but obviously you or your friend, you're standing in different locations. So we have to estimate the relative pose between these two views. This, of course, is a long-standing problem in computer vision. It's called visual relocalization. Usually it consists of two stages. You have a mapping stage and you have a relocalization stage. Mapping stage means you collect many images of the scene where you want to relocalize in, and then you build a visual map of the scene. When you have done that, when the mapping is done, you can relocalize. So given a new view of the same scene, you can register this new image to the existing map. And this is what we want to do, right? And you can solve this with traditional methods. We are able to do this for 20 years now with very good accuracy. So for example, on your mapping data, you can run ColMap, create a sparse point cloud with high dimensional descriptors, and you can use feature matching to register a new query image. This is what it looks like if you use feature matching. So you have your query image. First thing you have to do is so you map many places of the world. You first have to figure out which map is relevant to you. You can use image retrieval or maybe GPS signal to figure out which map do you want to relocalize to. And then you can use feature matching. So you extract features, you match them across the images. And because you have already reconstructed your mapping data, the 3D points the 3D coordinates of the feature points in the mapping image, which gives you 2D, 3D correspondences of the query to the map. And using Ransack and pose solver, you can estimate the pose. This is what we want. But is it instant? Well, no, not really, because if you have a lot of mapping images and you run ColMap, that takes quite a bit of time, or can take quite a bit of time. So we can look at maybe other recipes for visual relocalization and see how they would perform. So one that I want to talk about is scene coordinate regression. The pipeline looks very similar. The only thing that we change is that this feature extraction and matching step has been merged into correspondence regression. So we start again with a query image. This time, here's in this example, it's an indoor scene. And we have a network. The network is the scene representation. It is an implicit representation of the scene. There's no explicit 3D point cloud, but the network has been trained with your mapping data. So with mapping images and ground truth poses, and it learns an implicit representation of your scene. What the network predicts is a dense image of scene coordinates. It means that for every 2D pixel of the input image, it predicts the 3D location in scene space, which means the prediction itself is a dense 2D, 3D correspondence field. You can apply PNP and Ransack or pose solver and Ransack as before, which gives you the pose. Is this instant? Well, 2 years ago, the answer would have been no. You have to train a network per scene, which takes hours or days, right? In CVPR last year, we were able to show that you can do this actually quite quickly. You can train a network in a few minutes and still achieve very good accuracy, despite the need to train this network per scene. You can just do it very quickly. This assumes that you have the mapping poses of your mapping images already. Sometimes that is the case when you do real-time SLAM on the phone, for example, but sometimes it's not the case. And very recently, we were able to show that this ACE relocalizer that I just showed can also be trained in a self-supervised fashion. So you start with a single image and a depth estimate, you train the relocalizer, you use it to log on more views, you add this to your training data of the relocalizer, and you retrain. And you do this in a loop until you have mapped your complete mapping images. This is quite exciting because this turns the ACE relocalizer into a learning-based SFM model, basically an alternative to ColMap, which does not do any image-to-image matching. It directly learns to regress image-to-scene correspondences, which has some nice properties. For example, it scales very well in the number of images. You can reconstruct 10,000 images in an hour on a single GPU, which is nice. But is it instant? Well, let's assume we have the mapping poses. So we can train in a few minutes, and maybe you can train it even faster. So here you see a mapping run of the A3 localizer in 10 seconds. But this is really real time, what you see here, real time mapping. And still we can relocalize with high accuracy. 10 seconds, is it instant? Yes, but I would say no. It's not instant, it's not what we want. But because imagine you are out there with your friend, what do you have to do? You have to take the mapping images. You have to go around with your phone, you have to record all the data, and you have to take the scan itself, which makes it not instant. Okay. So we are back to our two images and back to our problem. We go through the literature again and see what else can we do. Traditional computer vision has still something for us. We can do post-triangulation. So we can do feature matching, 2D correspondences. We can estimate the essential metrics, decompose it, which gives us the relative pose, exactly what we want. Unfortunately, it's only up to scale. So we don't know the distance between the two cameras. Is this important? Yes, it is important. Because in our example, it does not only the true distance of the cameras, that it does not only influence the scale of the asset that we want to draw, it also influences the position of it. So the balloons could be anywhere if you don't handle the scale ambiguity. So one way out of it is to assume, well, if we have a third image, we can estimate a second relative pose, which gives us two directions of the translation vector, and then we can triangulate the pose, which resolves the scale ambiguity. The problem is that it becomes more robust and more accurate depending on how many images you have. So the minimum is 3. It will work in theory, but in practice, it will be extremely brittle and inaccurate. So the more images you have, the more practical it becomes, but then you're back to, well, you have to take a scan of the place. You have to collect many images. So different approach. And now learning comes into play. We take a scale metric depth estimation model, which gives us a metric depth estimate for our two images. If we then do feature matching, we don't have 2D correspondences anymore, but 3D correspondences, and we can estimate the relative pose without the scale ambiguity. Great. And this actually also works in practice. So here you have superglue feature matches between the reference and query images. Here you see the corresponding depth estimates of DPT in this case. And if we combine the two, we actually can estimate the relative pose between these two images, including scale. And I want to appreciate this fact. We have a single image of a place, and we have a scene agnostic learned model, which conditioned on the single image induces a scale metric space around it. And this allows us to register a different query image, an unseen image, to the reference space. And that's pretty exciting from a relocalization perspective. And we were so excited about it that we gave it a name, that we rebranded this type of relative pose estimation and called it map-free relocalization. This was a ECCV 2022 paper, and quite some people were involved in this work. Why did we need so many people? Well, I've shown you one example where it works, right? But we wanted to know, how well does it work? Does it really work in practice? So we collected a data set. We looked for places where this type of relocalization could work. Places where a single image is enough to represent this place well. And we asked users to go out and scan such places for us. And they did. They scanned a few places for us, a few hundred scenes. Each of them was scanned twice. We ran CallMap to reconstruct these images and register the two scans together. Everything is in scale metric space because we have IMU information from the phones. So if nothing of this is interesting to you, we have 460 SFM models online and scale metric units. Maybe that at least is useful to some of you. So each place was scanned twice by potentially different users who do different things. So here on the left, we see a user who scanned close to the statue and did a full 360 circle, whereas the user on the right scanned from further away. We split the data set into 460 scenes for training, 130 scenes for testing. The test ground truth is private. We have an online evaluation service so that you can tune your hyperparameters still. We have a validation set of 65 scenes where the ground truth is also available. For the training scenes, you get the full 2 scans. So you can sample pairs of images across the 2 scans. For test and validation scenes, we selected from the first scan 1 image, which is the reference image of this place. And the second image, the second scan you can use to pick query images. The dataset is quite diverse because the locations have been scanned throughout the world. And we have some nice statistics. So if you look at the time between scans, roughly 25% of scans were taken on the same day, maybe by the same user. 25% were taken within the same week, 25% within the same month, 25% within half a year. So we have some season changes, for example, in the dataset, although these are urban environments where the season change is not so dramatic in practice. We have a nice distribution over visual overlap. So we have some easy image pairs where the overlap between the 2 images is very high, but we also have very difficult image pairs where the overlap is very low. And you see in the diagram, there's a peak at 0 overlap. So we have seemingly impossible image pairs as well. And I will talk about this in a bit. So why does it happen? Because if you fix one reference, parts of the query scan just don't see the same structure as the reference anymore. And then the overlap is 0. And in terms of translation and rotation difference between the 2 images in the data set, here's a graph. One way to read this graph is to look for the median. So 50% here, and I would say 50% or the median in translation difference is like 3 meters, and in rotation difference, 40 degrees, I would say. So 50% of pairs have more and 50% of pairs have less. And here we see one example where the reference is very close up and the query images are very far away. So quite a scale change to bridge here. Okay, that's the data set. Let's see some results. I already showed you how we can use superglue and DPT to enable this capability. And here we see one more example where it actually works. So we have the reference image, the query image is here shown in blue, and the estimate of superglue and DPT. And we see it's quite close to the ground truth. And it traces out a nice trajectory. It looks very plausible. But this is a very easy scene of this data set. There are much more difficult cases and some nice challenges. Challenge number 1, large viewpoint changes. So here we see in the query scan that we take a 360 circle around the statue. And at some point, the feature matcher breaks down. We don't find correspondences anymore. And the pose estimate in yellow here spirals out of control. Tough. Challenge number 2, scale prediction. This time, the depth estimation model fails. Because this is pedestrian data. Back then in 22, we didn't find many metric depth estimation models that work on this type of data. And in some of these scans, there are really just very, very subtle cues about what the scale could be. In this case here, if you look at the yellow pose estimate, the orientation is fine. The feature matcher works, but the translation vector is, the translation is incorrectly scaled because the depth estimation model fails to estimate the scale of the scene. Challenge number 3, higher level reasoning. This is one of my favorite examples of the data set. You have a sign. We start at the front of the sign. Okay, we go around it. As we go around it, there's a nasty surprise because the back of the sign has the same text as the front of the sign. So any feature matching method will happily latch onto this text. It's the same. So it will tell you, yeah, you are the front of the sign, but no, you are not. And in order to figure it out, you can, for example, look at the background to figure out it cannot be the same side. and you have to do some reasoning, right? Cool. And last challenge, challenge number 4, we need a reliable confidence. What do I mean? Well, let's look at this scan here. We have the reference image, and now the query appears, and the user of the query image was just exploring the environment. So in times they are looking completely apart. It will be very hard, if not impossible, for any method to estimate the correct pose here, right? So should we include these images from the dataset? I would say no, because this, of course, can happen in practice. If we deploy such a capability, then the two users might look completely different directions. The worst thing that can happen is that the system just predicts a random pose, right? The system has to tell the user, I cannot do anything, sorry. You cannot estimate anything. So the method not only has to predict the pose, it also has to predict a confidence in its own prediction. So we are very excited about this problem. We deployed some baselines, but we are also interested in how far we can push it and how far you can push it. So we are organizing a workshop and a challenge in ECCB 2024. And we invite you to participate. The information you will find here when you follow this, QR code. There's an online leaderboard. This is what it looks like. We have some entries already. So why should you care of the depth estimation challenge? Well, there are instances here in this data set where just coupling an existing feature matcher with better depth estimates gains you ranks on the leaderboard. So for example, you have here Lofter, when you couple it with DPD, you have a certain rank, and then you gain 1 rank if you just couple it with KBR++ instead. And a more extreme example, DPT with Roma is rank 8 on this leaderboard, but if you couple it with depth maps of a method which is called Mickey, then you jump to the 2nd place of this leaderboard. And as an extra motivation, we created a 2nd leaderboard. Now there's a 2nd track, which is called multi-frame. You still have 1 reference image, but instead of a single query image, you have a burst of frames as a query with relative tracking poses between them. So if you work on multi-frame depth estimation, this leaderboard is for you. And as you see, it's empty. We just provided a single baseline, which is a single view the baseline. So it's very, very easy to achieve something on this leaderboard. Cool. So back then in 2022, what we did when we created the data set, we tried some baselines. We took off-the-shelf models, we taped them together and saw how well they worked. But of course, that's not ideal, because if you couple feature matching with depth estimation, they don't know each other, right? They were not built for each other. They don't know what the other model is doing. So we tried to come up with a solution where depth estimation and feature matching are integrated within 1 pipeline and trained jointly. And this is Mickey, which is an oral here at CVPR. Axel can give you a great talk tomorrow in the oral session. And now I share my perspective on this work here in a few minutes. So the pipeline is inspired by feature matching, 2D feature matching. It looks very similar. We start with 2 images and we predict key points. But the key points are 3D key points. They live in metric space. They are metric. And for each 3D key point, we have a high dimensional descriptor, so we can do feature matching. These correspondencies are now 3D, so we can apply RANSAC and a pose solver to get a scaled metric pose. And because our key points are metric, so are our relative poses. Okay, cool. How do we train this network? We can look at 2D matchers and see how are they trained. They are usually trained by strong supervision using ground truth correspondencies. Because we have 3D correspondencies, we need ground truth 3D correspondencies. How do we get them? Well, first thing is we need matchable image pairs, right? We need some images where we know we can establish ground truth correspondences. Good. Then we can start with, okay, we do the same as other methods. We establish ground truth 2D correspondences. This usually works by taking key points or points in the first image and projecting them to the other image. For this projection, we need the relative camera pose and we need metric depth. Here's where the trouble starts because we don't have depth for these images. These were collected with phones without LiDAR. So we can use maybe a strong teacher model somehow, a good depth estimation model, which we then use as pseudo ground truth, but not ideal. Another issue are difficult image pairs like this. These are image pairs which we would like to solve. It's possible, right? You would look at this image and would say, yeah, it's probably the same statue. One is from the front and one's from the back. But how do you define ground truth correspondences here? Because the front of the statue is not visible in the other image. It's self-occluded by the back of the statue. And the last difficulty here is, well, common metrics of visual overlap would probably fail here. They would predict a low overlap and we would probably dismiss this image pair. So we would have to come up with a new visual overlap metric, which tells us, yeah, this is a solvable image pair. So our solution to all of these question marks was, oh, no. No, we don't do any of that. No, we have to make do with the relative poses. This has to be enough. How does it work? Or first question, does it work? Yes, it does work. So we, at the end of what I explain next, this is what comes out of it. And it's quite interesting because with only this relatively weak high-level supervision of relative poses, what Mickey learns to do is to reason about the shape of the prominent object in the scene. It recognizes, oh, there's a statue, and I try to match the top of the head of the statue and the left shoulder to left shoulder, right shoulder to the right shoulder. If you compare this to 2D matchers, because of how they have been trained, it's very different. They latch onto the co-visible surface, which is here in the background, and they try to figure out which symbol matches which symbol between the two frames. I think that's quite interesting, this different emergent behavior of the two models. Okay, how does it work? Well, I presented the forward pipeline to you. And the end of this pipeline is the relative pose, right? And we have relative pose ground truth. So what's the problem? We can just apply a loss, right? And then differentiate, so propagate the gradients back through the pipeline. This is how we could train it. It's not so easy because you have ransack here, and then there's feature matching is all discrete, but it's not impossible, right? There have been works, and I was involved in some of them, to show how this can work. Differentiable ransack, differentiable feature matching, these methods exist. And now we use them. I will explain the gist of how this works here on the slide. The real system is a bit more complicated. Here is a simplified version just to show what the idea is. So we have discrete matches and we want to train them. Problem is that they are discrete. So if I have a key point and I want to match to key point A, or I want to match to key point B, there's no easy way to make it soft. It's either A or either B, right? So the idea behind it here is to assume you have an exhaustive matching. All matches exist. You match everything to everything. All matches are there. They only have different probabilities. So you define a probability distribution over possible matches. The probability is derived from the descriptor distance. If two descriptors are close, then the match probability is high. If they are far apart, then the descriptor probability is low. And this is how you can make it soft. Switching from matching A to matching B just means reducing the probability to matching A and increasing the probability to matching B. So how can we now train this using post-supervision? Well, we just sample matches. So from this probability distribution, we discretely select matches and have a concrete sample of, or a concrete matching sample from which we can calculate a pose. And we do it again. We sample again, we get a different estimate of the pose, and we do it again, a different estimate of the pose. And we do this many, many times. We have many samples of poses. And now we can apply our loss, and the loss pulls all the samples towards the ground truth. And what it will do with the matching probabilities is for matchings which resided in a good pose, you want to increase the probability of these matches. And for matches which resided in a bad pose, you want to decrease the probability of these matches, which then shapes the descriptor space. Bad descriptors are pulled apart, good descriptors are put together. And this is the main idea. Does it work? Yes, it works. So this is the result that we get, and we see that we indeed can predict key points in 3D and match key points in 3D. And the model is also able to bridge quite extreme viewpoint changes. Also, it does relatively good in scale changes. So if you start from further away and then you go closer to the statue, that's also working nicely. And here's a very extreme example. 2 images, if you stare at them long enough, you would probably figure out, well, it's opposing views, opposing shots of the same structure. And Mickey is able to figure it out, right? Other methods, they struggle. So because they only do 2D matching, they collapse to the same side or they fail completely. And one nice property of all these feature matching solutions is that you can count the inliers, and this gives you a confidence. And in the Mickey differentiable pose optimization framework, there's also a signal going to the inlier count to help train it in the procedure. And we see that as we go behind this sculpture or whatever it is, Mickey struggles to predict a good pose, but at least it tells you, right? There's a low confidence. To reinforce the justification to be here, standing here in the monodepth estimation challenge and workshop, here is depth estimation result of Mickey. So this is now a bit awkward because I've seen in all the talks, I have seen amazing, crisp and detailed depth estimates. And you might look at this and say, well, dude, to be honest, it looks quite crap. But remember, this was trained without any direct supervision of on the depth maps. And it was trained in a way to say, we don't need correct depth everywhere. We just need correct depth where we want to sample key points. And that through the differentiation of feature matching and ransack, we still see this plausible and nice depth maps emerging. I find it quite exciting. So how do we do with our initial vision of enabling instant AR everywhere? I think we are doing pretty good. So here we see again an example with the balloons. And here are Mickey estimates where we use Mickey to project this AR asset into different views. There's no tracking, right? These are individual estimates. And it's quite decent. It's nice. And especially, I want to emphasize the progress that we have made. So the best method of ECCV 2022 is on the left. The best method of CVPR 2024 is on the right. And quite some progress that we made in basically 1 year, maybe 1.5. And as we speak, there's another method throning on the leaderboard, a paper from Aver, which was just, the archive came out just before this CVPR. And it basically, in terms of numbers, the step forward that we see here, they made another step with the same magnitude. And these results are also very exciting. And we are very excited to see whether you can help us push this even further. Again, I invite you to participate in this challenge, ECCV 24. And that's the end of the talk. Thank you so much. We might have time for questions, or you catch me at the conference. Dimitro?
Very stupid question. So what's your intuition like? Let's say you have some data sets like partially, you say like good depths, and maybe you can add this supervisory signal But on the other hand, like it would force on the things which you are not interested in because they're like not using this like good key point matches and so on. So like, would it help in your paradigm if you add like another was for part data set, or it's actually not, and it's better go fully like full supervised?
I think it would help. So the problem, the way this is trained is reinforcement learning, right? We have been able to train it from scratch like this on a relatively small scale data set. I mean, the map-free data set is nice, right? But it's just a few hundred scenes, and there are larger data sets out there. I think the way to go is to harvest these larger data sets and the annotation when you have it, pre-train it like this, and then use the reinforcement learning approach just to fine-tune it. I think that will give you the best approach. There's always the danger that with pre-training, you think in the local minima that you can't escape anymore. But I think ultimately my intuition would be, in this case, probably it works out better if you do it like this.
How are the key points selected and how many is enough?
This is a question for the main author, which is also in the audience. I think it's like 1,000, 2,000 key points, which are randomly sampled. Is that correct, Axel? 2,000?
Is 2,000 and then 500.
Yeah. Okay, so we select 2,000 key points. They are randomly selected according to the confidence, which is predicted by the network. And then from these, you sample 500 correspondences to calculate the pose. Or yeah, first from the audience, I think.
Have you experiment this on larger scenes like landmarks?
No. So we for this paper we really just stick to the map-free data set, scanner data set. But again, Axel, did we try it on larger data sets? No.
Even more reps to stay away from
So we haven't tried. This new leaderboard is really just went up a few weeks ago for the challenge. I think so. You have multiple frames, and you also have the tracking poses from the phone for these frames, which should help a lot with the scale estimate of the scene. But it will not help you to bridge these extreme viewpoint changes. So I'm personally looking. I'm curious to see how much it helps. I think it will help to some part, but it will not help you solve it because there are other challenges that you still have to address.
So were you able to train Mickey on data sets that usually people don't train on because they don't have that?
You would think that it is possible, but we haven't tried it. I think we should. We should just scale it up. We focused on the map-free data set, but the thing to do is to scale it up massively. We know we have many like observations like this. Scale it up, it will work better. So there's no reason to not do it.
So you have a many-to-many association, which you call a soft association, which is based on distance. How do you prune between a high confidence distance, which is farther away, but a low confidence distance with match between, which is like closer?
I'm not sure I understand the question. So we just randomly sample, and then if the matches are bad, then the sample will be bad. So is this going in the direction of your question, or?
So you have a set of matches from both images, right?
Yes.
And then you look at the match and you calculate the distance between those matches, which is proportional to some probability, because they're farther, you give it a lower probability. Is that right, the way I understood it?
So we calculate the descriptor distance between two key points that we match, and then it's a softmax over all matches. So this is how we get the probability.
So I'm sorry, then I understood it as a 3D distance between those two, but it's basically a key point distance.
It's a key point distance, yes.
So for Nikki and the 3D key points that you predict, should we really be thinking about the key points as basically, like a depth map armed with with some feature, or are the key points kind of free to appear, somewhere in space as long as it maximizes basically the, or I should say minimizes the loss during training?
I love the question because in a sense, I personally was a bit disappointed to see the depth maps emerging because I was hoping that the network is free to do something like latent or semantic key points almost, right? To not restrict itself to the surface, but to do anything, right? But the Mickey architecture does not have cross attention. It's a purely single image network which predicts descriptors and key points and so on. So I think for this to happen, what you explained, it would need cross attention. When we started the project, we decided against cross-attention models because we thought, well, if you want to use it for SFM, then it's better if it doesn't have cross-attention because you can just apply it to images. But then we didn't have really time to explore it. We restricted ourselves in the paper to the map-free problem, where you could have used that cross-attention, but we didn't. So, I mean, for the challenge, would be a good opportunity to explore that.
Thank you.
Okay.
I wanted to plan to scale up the training for the Mickey upline because currently on the leaderboard, the top one master is probably use a lot more data during its training.
It was trained on a lot more data and it has cross attention. So it would be really interesting to see if you level it out between the two approaches and train Mickey on more and maybe add cross attention to it, what comes out on top? But we don't know. Okay, I think we don't have questions anymore. So thank you again for having me. It was fun.
Great talk.
Thank you.
You guys are the new wave of feature.
Thank you. I selected it for the occasion.
Yeah.
Good to meet you in person.
Yeah, same here. Same here. I'm a big fan of your Twitter tweets.
Likewise.
Keep tweeting. Keep tweeting.
I will. Thank you.
All right.
All right, so that's a wrap online as well. Thank you everyone for attending.
Thanks everyone.
We'll probably see you next year.
Great. Thank you everyone. See ya.
Thank you everyone.